A star dies. It doesn't explode. It doesn't collapse into a black hole. It becomes something stranger. A cosmic diamond the size of Earth, weighing as much as the sun, glowing white-hot in the silence of deep space. And inside it, nothing is burning, no fusion, no fuel, no energy source at all. Just a quantum mechanical rule from the 1920s holding back total annihilation. White dwarfs are dead stars. Stellar corpses packed so tightly that a single teaspoon of their matter would weigh 5 tons on Earth, 1 million times denser than our planet. Dense enough that atoms themselves are crushed out of existence, and yet, somehow, impossibly, they do not collapse further. They sit there, stable, supported by nothing but the behavior of electrons, obeying a law most people have never heard of. This is not gravity losing. This is not magic. This is quantum mechanics doing something so fundamentally strange that when a young physicist named Chandrasekhar first calculated it in 1930, the scientific establishment refused to believe him. They told him he was wrong, that his math had to be broken. Because what he was describing, a boundary where stars could no longer exist, where matter itself gives up, sounded like science fiction. But he was right. And that boundary, the Chandrasekhar limit, 1.4 solar masses, is the razor's edge between existence and catastrophe. Cross it, and the star doesn't just collapse, it detonates. A Type 1a supernova. An explosion so bright it can outshine an entire galaxy for weeks. In the far future, when every star has burned out and the universe goes dark, white dwarfs will be the last lights left, glowing embers in an ocean of cold and silence. This is their story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe does not tolerate waste. Every atom that has ever existed will eventually be put to work somewhere, doing something, whether it likes it or not. Stars are no exception. They burn for millions or billions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, climbing the periodic table one nuclear reaction at a time, and then, inevitably, they run out of fuel. What happens next depends entirely on how much mass the star started with. And for the vast majority of stars in the Milky Way, what happens next is not what you'd expect. When most people think about the death of a star, they picture one of two endings. Either the star explodes in a supernova, a violent detonation so bright it can outshine an entire galaxy for weeks, leaving behind a neutron star or a black hole. Or the star simply fades away, growing dimmer and colder, until it becomes an invisible corpse drifting through the void. Both of those endings are real. Both happen all the time, but they are not the most common outcome, not even close. 97% of all stars in the Milky Way will end their lives as something stranger, something that defies the basic logic of gravity. Something that sits in a kind of cosmic no-man's land between total collapse and total dispersal. They will become white dwarfs, and the fact that white dwarfs exist at all is one of the most unsettling puzzles in astrophysics, because by every intuitive rule, they shouldn't. Here's the problem. A star is a balancing act. For as long as it's alive, two forces are locked in a constant tug of war. Gravity is pulling everything inward, trying to crush the star into the smallest possible volume. Nuclear fusion in the core is pushing outward, generating heat and pressure that resist that crush. As long as the fuel lasts, the two forces stay roughly equal. The star holds its shape. It radiates light. It behaves like a star. Then the fuel runs out. When a star exhausts its supply of hydrogen, the core contracts and heats up until it's hot enough to start fusing helium. When the helium runs out, the core contracts again and the star starts fusing carbon. For massive stars, those with at least 8 times the mass of our Sun, this process keeps going. Carbon fuses into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage produces less energy than the last. Each stage burns faster than the one before it. A star can spend millions of years fusing hydrogen and only a few days fusing silicon. By the time iron starts to pile up in the core, the star is out of options. Iron doesn't release energy when it fuses. It absorbs energy. The moment iron forms, the outward pressure vanishes, gravity wins. The core collapses in less than a second and the star explodes. That's the supernova route. It's violent, it's spectacular, it produces neutron stars and black holes and scatters heavy elements across space to seed the next generation of stars and planets. It's also reserved for the heaviest stars, the ones born with more than about 8 times the mass of our Sun. Those stars are rare. They make up less than 3% of all stars that have ever formed in the Milky Way. The other 97% don't have enough mass to reach the iron stage. They burn hydrogen, they burn helium. Some of them manage to fuse a little carbon, and then they stop. Not because they explode, because they simply can't get hot enough to continue. When one of these lighter stars runs out of fuel, something strange happens. The core contracts under its own gravity, just like in the massive stars. But instead of collapsing all the way into a neutron star or a black hole, it stops. The collapse halts at a size roughly comparable to Earth. The outer layers of the star, no longer supported by the pressure from below, drift away into space, forming a glowing shell of gas called a planetary nebula. And what's left behind, sitting at the center of that expanding cloud, is a white dwarf. A star-sized mass compressed into a planet-sized volume. No fusion, no internal heat source, just a dead ember cooling slowly in the dark. The first white dwarf humanity ever identified was Sirius B, the faint companion to Sirius, the brightest star in our night sky. Sirius A is impossible to miss. It's brilliant, blue-white, sitting prominently in the constellation Canis Major. If you've ever looked up on a clear winter night in the northern hemisphere, you've seen it. What you probably didn't notice is that Sirius A has a companion, a tiny dim object orbiting it every 50 years. Astronomers noticed the wobble in Sirius A's motion in the mid-1800s and deduced that something massive was tugging on it. In 1862, the telescope maker Alvan Clark spotted the companion for the first time while testing a new lens. There it was, Sirius B, a faint point of light sitting right next to one of the brightest stars in the sky. At first, astronomers assumed Sirius B was just a normal faint star. But in 1915, Walter Adams at Mount Wilson Observatory managed to capture its spectrum, the breakdown of its light into individual wavelengths. What he found made no sense. Sirius B was hot, extremely hot. About 3 times hotter than Sirius A. If it was that hot, it should have been bright. Stars that hot are always bright. But Sirius B was dim. Impossibly dim for its temperature. The only way to explain that combination of heat and faintness was if Sirius B was tiny, not just small, Earth-sized, and if something with the mass of a star was compressed into the size of a planet, the density would be incomprehensible. The word incomprehensible gets thrown around a lot when people talk about space. Black holes are incomprehensible. The size of the universe is incomprehensible. Most of the time, it's hyperbole. With white dwarfs, it's not. The density of these objects breaks every analogy you try to build. A typical white dwarf has about 60% the mass of our Sun packed into a sphere, roughly the size of Earth. Earth has a radius of about 6,370 kilometers. The Sun has a radius of about 700,000 kilometers. A white dwarf takes the Sun's mass and squeezes it down into something you could, in theory, drive across in a few hours if there were a road and you didn't immediately vaporize from the heat. The result is a density of about 1 million grams per cubic centimeter. 1 million. A sugar cube-sized chunk of white dwarf material would weigh about a ton. A teaspoon would weigh several tons. If you could somehow stand on the surface of a white dwarf, which you absolutely could not because the gravity would pulverize you into a thin smear of atoms, you would weigh about 50 million pounds if you currently weigh 150. The surface gravity is somewhere between 100,000 and 350,000 times stronger than Earth's. Drop a pebble and it would hit the ground at a speed that would make a bullet look like it was standing still. White dwarfs are not the densest objects in the universe. Neutron stars are denser. Black holes, if you can even call the singularity inside them an object, are theoretically infinitely dense. But white dwarfs are dense enough to make everything you think you understand about matter stop making sense. And they are dense in a way that shouldn't be stable. Gravity should not stop at planet-sized. Gravity should keep pulling. The mass should keep collapsing. The atoms should keep compressing until there's nothing left but a singularity. That's what gravity does. It doesn't compromise. It doesn't pause. It crushes until there's nothing left to crush. Except in a white dwarf, it does pause. Somehow, these objects have found a way to resist gravity without using heat, without using nuclear fusion, without using any of the tools that keep normal stars inflated. They just sit there, defying the most fundamental force in the universe, holding their shape for trillions of years. And for decades after Sirius B was discovered, nobody could explain how. The problem is that intuition doesn't scale. Your brain understands the world at human-sized densities. You understand that a rock is denser than water. You understand that metal is denser than wood. You might even understand that the core of the Earth is denser than the crust. But your brain has no framework for understanding a place where the atoms themselves have been crushed into each other so tightly that the normal structure of matter ceases to function. At the densities inside a white dwarf, atoms don't exist the way they do on Earth. The electron clouds that normally surround atomic nuclei, giving atoms their size and their chemical properties, have been squeezed into a state where they overlap. The nuclei, the tiny dense kernels of protons and neutrons at the center of each atom, are still there. But the electrons have been forced into a kind of quantum traffic jam where the normal rules no longer apply. Under normal circumstances, if you try to compress matter, the atoms push back. Squeeze a balloon and it resists. Squeeze harder and eventually it pops. The resistance comes from the electromagnetic force, the repulsion between the negatively charged electron clouds surrounding each atom. Atoms don't like being too close together. They have personal space requirements. Push them together and they push back. That's what gives normal matter its solidity. That's why you can't walk through walls. The electrons in your hand and the electrons in the wall refuse to occupy the same space. But inside a white dwarf, the pressure is so extreme that normal electromagnetic resistance isn't enough. The gravity is pulling with such force that the atoms are being crushed far beyond the point where their electron clouds would normally push back. The electrons are being forced so close together that the spaces between them vanish, and at that point, something else has to step in. Some other force has to stop the collapse. Otherwise, the star would keep shrinking until it became a neutron star or a black hole. And for stars below a certain mass, that's not what happens. They stop at white dwarf size, they stabilize, and they stay that way. For more than a decade after Sirius B was discovered, nobody knew why. The best physicists of the era stared at the numbers and couldn't make them work. If a white dwarf was as dense as the observations suggested, it should collapse. The fact that it didn't meant something was missing from the physics, something fundamental, something nobody had thought of yet. The answer, when it finally came, didn't come from astronomy. It came from quantum mechanics. And it came from a principle so strange, so counterintuitive, that even the physicists who discovered it struggled to believe it was real. The principle is called the Pauli exclusion principle, named after Wolfgang Pauli, who formulated it in 1925. It's one of the foundational rules of quantum mechanics, and it says, in plain terms, that no two electrons in the same system can occupy the exact same quantum state. They can't have the same position, the same momentum, the same spin, all at the same time. If you try to force two electrons into the same state, they resist. Not because of electromagnetic repulsion, not because of any force you can measure directly. They resist because the universe simply does not allow it. And that resistance, that quantum refusal, is what holds up a white dwarf. Inside a white dwarf, the electrons have been compressed so tightly that they are forced into the lowest available energy states. There's nowhere else for them to go. And because no two electrons can occupy the same state, they start piling up in higher and higher energy levels, like passengers being forced onto an overfilled subway car. The pressure that results from this piling up is called degeneracy pressure. It has nothing to do with heat. It has nothing to do with motion. It is purely a consequence of quantum mechanics refusing to let electrons overlap, and it is strong enough to hold up the entire mass of a dead star. That realization changed everything. It meant that white dwarfs weren't just strange astronomical curiosities. They were laboratories for testing the limits of quantum mechanics at scales no human experiment could ever reach. A white dwarf is what happens when you take the rules that govern atoms and electrons in a lab and scale them up to the size of a planet. And the fact that they don't collapse means the rules hold. Quantum mechanics isn't just a theory that works in particle accelerators. It's the law that keeps dead stars from vanishing into singularities. But there's a catch. Degeneracy pressure has a limit, and that limit is what separates a white dwarf from something far stranger. The problem with understanding white dwarfs is that nobody alive today will ever watch one form. The process takes longer than human civilizations have existed, longer than written language, longer than our species has been walking upright. You can't point a telescope at a star and say, "Watch this, it's about to become a white dwarf." You have to piece together the story from snapshots, from hundreds of stars caught at different stages of the same slow collapse, and assemble them into a timeline that spans tens of millions of years. What emerges from that timeline is a story that defies every intuition you have about how things are supposed to end. Our sun is going to become a white dwarf. Not today, not tomorrow, not for another 5 billion years, but it's coming. The process is already baked into the physics. The sun has been burning hydrogen in its core for about 4.5 billion years, fusing it into helium at a rate of about 600 million tons per second. That sounds catastrophically wasteful until you realize the sun weighs 2 times 10 to the 30 kilograms. At the current burn rate, it has enough hydrogen to keep going for another 5 billion years before the core runs dry. When that happens, everything changes. The core contracts. Gravity, which has been held at bay by the outward pressure of fusion, finally gets its way. The hydrogen shell around the inert helium core heats up as it compresses and starts fusing on its own. The energy from that shell fusion pushes the outer layers of the Sun outward. The surface cools, the Sun swells, it becomes a red giant. Over the course of a few 100 million years, the Sun will expand to roughly the orbit of Mars. Mercury will be swallowed, Venus will be swallowed. Earth's fate is less certain. Some models say it gets engulfed. Others say it survives, stripped of its atmosphere, scorched to a lifeless cinder, orbiting the bloated dying star at the edge of annihilation. The red giant phase is not a stable configuration. The Sun will shed mass, a lot of it. Stellar winds will peel away the outer layers and carry them into space. Astronomers estimate that by the time the Sun finishes this phase, it will have lost somewhere between 30 and 40% of its total mass. The remaining core will keep contracting. When the temperature hits about 100 million degrees, helium fusion ignites. 3 helium nuclei fuse into carbon. 2 heliums fuse into beryllium, which immediately captures another helium to form oxygen. This is called the triple alpha process, and it's where white dwarfs get their composition: carbon and oxygen. The ashes of helium burning, piled up in the core like spent fuel rods in a reactor. For a star like the Sun, helium fusion lasts about 100 million years. That's roughly the same amount of time it took for dinosaurs to appear and then go extinct on Earth. When the helium runs out, the core contracts again. But this time, it doesn't get hot enough to ignite carbon. Carbon fusion requires temperatures above 500 million degrees. The Sun's core will top out at around 200 million, not even close. The fusion stops. The core is now an inert ball of carbon and oxygen, sitting at the center of a star that no longer has the mass or the gravitational pull to compress it any further. The outer envelope, no longer supported by fusion pressure, begins to drift away, slowly at first, then faster. The stellar winds intensify. Over the course of tens of thousands of years, the entire outer shell of the star peels off and expands into space, forming a glowing cloud of ionized gas called a planetary nebula. The name is misleading. It has nothing to do with planets. When these objects were first observed in the 18th century through small telescopes, they looked round and fuzzy, like the disks of distant planets. The name stuck, even after astronomers realized they were looking at the discarded atmospheres of dying stars. Planetary nebula are some of the most beautiful objects in the night sky. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco. Each one is a star's final breath, a shell of gas expanding outward at tens of kilometers per second, lit from within by the ultraviolet radiation from the dying core at its center. They last for about 10,000 years before the gas disperses into the interstellar medium. 10,000 years is nothing. Blink and you miss it. Most of the planetary nebulae we see today were formed while humans were still figuring out agriculture. And sitting at the center of every planetary nebula, exposed for the first time in its life, is the core, the white dwarf. What's left is small, roughly the size of Earth. The mass is not small. The core still weighs about 60% as much as the entire Sun did when the process started. That's about 2 times 10 to the 30 kilograms compressed into a sphere with a radius of about 6,000 kilometers. Do the math, and the density comes out to roughly 1 million grams per cubic centimeter. 1 million. That number needs to sit for a second because your brain will try to smooth it over. Here's what it means. Take a sugar cube, 1 cubic centimeter. On Earth, that sugar cube weighs about 1 gram. On a white dwarf, that same volume would weigh 1 million grams. 1,000 kilograms, a metric ton. You could lift a sugar cube on Earth. You could not lift a sugar cube of white dwarf material. You couldn't move it. You couldn't even dent it. If you somehow placed it on the ground, it would sink through the floor, through the foundation, through the bedrock, and keep going until it hit the core of the planet. The temperature at the surface of a freshly formed white dwarf is around 100,000 degrees Kelvin. Hot enough to ionize any atom that gets near it. Hot enough to emit intense ultraviolet radiation. That's what lights up the planetary nebula. The core itself is even hotter. Temperatures inside can reach 10 million degrees or more in the first few thousand years after formation. That heat is left over from the compression. When the core collapsed under its own gravity, the atoms were squeezed so tightly that their kinetic energy spiked. The core didn't get hot because something was burning. It got hot because it was crushed, but there's no fuel left. No fusion, no internal energy source to replace the heat as it radiates away. A white dwarf is not a star in the traditional sense. It's a cooling ember. The only reason it glows at all is because it hasn't had time to cool down yet. Give it a few billion years and the surface temperature will drop to 50,000 degrees. Give it a few trillion and it will cool below the point where it emits visible light. Eventually, in a span of time so long that no human language has a word for it, the white dwarf will fade to black. Astronomers call that final state a black dwarf. None exist yet. The universe is only 13.8 billion years old. That's not nearly old enough for any white dwarf to have cooled completely. The oldest white dwarfs we've observed are still glowing faintly in the infrared, still radiating the last traces of heat from a collapse that happened billions of years ago. The composition of a white dwarf depends on what the star managed to fuse before it ran out of energy. For stars like the Sun, the core is mostly carbon and oxygen. About 50% carbon, 50% oxygen, give or take. Stars slightly more massive than the Sun, those with initial masses between about 8 and 10 solar masses, can get hot enough to fuse carbon into neon and magnesium before they collapse. Those stars leave behind oxygen, neon, magnesium white dwarfs, rare, but they exist. Stars less massive than the Sun, the dim red dwarfs that make up the majority of stars in the galaxy, don't even get hot enough to fuse helium. If they ever reach the end of their lives, which they haven't yet because red dwarfs live for trillions of years, they'll leave behind pure helium white dwarfs. We've found a few of those already, formed not from single stars, but from binary systems where one star strips helium from its companion before the companion can ignite it. The size of a white dwarf is fixed by its mass in a way that seems backwards. On Earth, if you add more material to an object, it gets bigger. Build a taller building and it takes up more space. Add more water to a balloon and the balloon expands. White dwarfs do the opposite. Add more mass to a white dwarf and it shrinks. The reason is gravity. The more mass you pack in, the stronger the gravitational pull. The stronger the pull, the harder the core gets compressed. The harder it compresses, the smaller it gets. A white dwarf with 60% the mass of the Sun has a radius of about 7,000 kilometers. A white dwarf with one solar mass has a radius of about 5,000 kilometers. A white dwarf at the upper mass limit, about 1.4 solar masses, has a radius closer to 3,000 kilometers. More massive means smaller, denser, harder to survive near. The surface gravity of a white dwarf is somewhere between 100,000 and 350,000 times stronger than Earth's. If you weigh 70 kilograms on Earth, you would weigh about 14 million kilograms on a white dwarf, 14,000 tons. You wouldn't just be crushed, you would be flattened into a layer of atoms a few microns thick, spread across the surface like paint. Your atoms would still be there, technically, but you wouldn't. Anything that falls onto a white dwarf's surface hits with an impact energy measured in megatons. Meteors don't leave craters, they vaporize on contact, releasing bursts of X-rays. The escape velocity, the speed you'd need to achieve to leave the surface and never come back, is around 5,000 kilometers per second for a typical white dwarf. That's about 1.5% the speed of light. Rockets don't reach those speeds. Nothing built by humans reaches those speeds. If you were standing on the surface, which again you could not, the horizon would curve sharply. You'd be able to see the geometry of space-time bending under the sheer weight of the mass beneath your feet. Light itself would struggle to escape. Photons climbing out of the gravity well lose energy. Their wavelengths stretch. A white dwarf emits ultraviolet light from its core, but by the time that light reaches us, some of it has been redshifted into the visible spectrum. The star looks dimmer than it should, not because it's farther away, but because gravity is stealing energy from every photon that leaves. White dwarfs don't rotate fast. Most spin once every few hours or days. The sun rotates once every 25 days. When the core collapses, conservation of angular momentum should speed up the rotation dramatically, the same way a figure skater spins faster when they pull their arms in. Some white dwarfs do spin quickly. There's one called Epic 20571711486 that rotates once every 5.5 minutes. But most don't. The current theory is that magnetic braking slows them down. As the star sheds its outer layers during the red giant phase, the magnetic field threads through the expanding gas and transfers angular momentum outward, slowing the core before it fully collapses. By the time the white dwarf is exposed, most of its spin is gone. Some white dwarfs have magnetic fields, strong ones. Fields measured in millions of Gauss, thousands of times stronger than the most powerful magnets humans have ever built. These are called magnetic white dwarfs, and they make up about 10% of the population. The fields are fossil remnants left over from the star's main sequence phase and compressed along with the core during collapse. The field lines get squeezed into a smaller volume, and the field strength goes up. If the original star had a field of a few hundred Gauss, the white dwarf can end up with a field of 10 million. That field can channel material falling onto the surface, funneling it toward the magnetic poles and creating localized hotspots bright enough to emit X-rays. The surface of a white dwarf is not a place you can walk on. It's not solid in the way Earth's crust is solid. The material at the surface is in a strange state, an ionized plasma where the electrons have been stripped from their nuclei by the heat and the pressure. Below that, a few meters down, the pressure climbs high enough that the plasma starts to behave more like a solid. The atoms are packed so tightly that they lock into place, unable to move past each other. Deeper still, a few kilometers down, the pressure crosses a threshold where the electrons are forced into a degenerate state. That's the quantum traffic jam. The electrons can't overlap. They pile up in higher energy states. The material becomes incompressible by any normal standard. You could hit it with the force of a colliding planet and it wouldn't compress. Not because it's strong, but because quantum mechanics says no. The core is where things get truly strange. At the very center of the white dwarf, the pressure is so extreme that the carbon and oxygen nuclei are forced into a crystalline lattice. They arrange themselves into a repeating geometric pattern, like atoms in a diamond. Except this diamond is the size of a planet. The core of a white dwarf is not metaphorically a diamond, it is literally a diamond. carbon atoms locked into the same face-centered cubic structure that makes diamonds on Earth the hardest natural material. Oxygen atoms occupy a similar lattice interspersed with the carbon. The entire core solidifies over time as the white dwarf cools, starting from the center and working its way outward. Theoretical models predict that the oldest white dwarfs in the galaxy, those that have been cooling for 10 billion years, are mostly crystallized. A few have been observed with oscillations in their brightness that match the predicted behavior of a crystallizing core. The vibrations propagate through the solidifying interior like sound waves through a bell. Astronomers can measure those vibrations and map the internal structure of the star. It works the same way seismologists use earthquakes to map Earth's interior. The process of crystallization releases a small amount of latent heat, the same way water releases heat when it freezes into ice. That heat slows the cooling process slightly, extending the white dwarf's lifetime by about 1 billion years. Not much in the grand scheme, but enough to be detectable. Observations from the Gaia Space Telescope have confirmed that white dwarfs cool more slowly than models predicted, and the leading explanation is crystallization. The data matches the theory. The cores are freezing solid. One white dwarf in particular has caught the public imagination. BPM 37093, also catalogued as V886 Centauri, sitting about 50 light-years from Earth in the constellation Centaurus. It's a white dwarf with a mass of about 1.1 solar masses, slightly larger than average. The core is estimated to be about 90% crystallized. Astronomers have calculated that the interior contains roughly 10 billion trillion carats of diamond. That number is meaningless in practical terms. You can't mine it, you can't reach it, you can't even get close without being vaporized. But the fact remains. The largest diamond in the known universe is not sitting in a vault or a mine. It's floating in space, cooling slowly, waiting for the universe to end. The formation of a white dwarf is not a single event. It's a process, a long, drawn-out fade that begins when the star runs out of fuel and ends when the core is finally exposed, stripped of its envelope, left to cool. The timescale from the end of helium burning to the full dispersal of the planetary nebula is somewhere between 50,000 and 100,000 years, fast by stellar standards. A blink compared to the billions of years the star spent fusing hydrogen. By the time the nebula fades, the white dwarf is already ancient, already cooling, already beginning the long march toward invisibility. And yet, despite the collapse, despite the compression, despite the loss of 90% of the star's original radius, the white dwarf does not collapse further. It holds. Somehow, against all the weight pressing down on it, against gravity that should by all rights crush it into a neutron star or a black hole, it stops. The atoms are gone. The normal structure of matter has been obliterated, and still the core resists. The question is how? How does something this dense, this massive, this gravitationally crushed stay intact? The answer lies in the wreckage of the atoms themselves. The problem with trying to imagine the density inside a white dwarf is that your brain will fail you before you even start. Not because you're not smart enough, because the numbers involved are so far outside the range of everyday experience that there's no intuitive foothold to grab onto. You can read that a white dwarf has a density of 1 million grams per cubic centimeter, and your brain will file that away under very dense and move on. It will not register what that actually means. It will not build a picture. It will do what brains do when confronted with numbers they can't process. It will nod politely and think about lunch. So let's try again, slower this time. with the kind of detail that forces the picture into focus whether your brain wants it or not. Take a sugar cube, 1 cubic centimeter, small enough to fit on your thumbnail. On Earth, that sugar cube weighs about 1 gram, light enough to flick across a table. If you made that same sugar cube out of lead, the densest material you're likely to encounter in daily life, it would weigh about 11 grams, still light enough to hold in your hand without noticing the weight. If you made it out of osmium, the densest naturally occurring element on Earth, it would weigh about 22 grams. You could carry a pocketful and barely feel it. Now take that same cubic centimeter and fill it with material from a white dwarf. That sugar cube would weigh 1 million grams, 1,000 kilograms, a metric ton. You could not lift it, you could not budge it. If you placed it on a table, the table would collapse. If you dropped it on the floor, it would punch through the floor, through the foundation, through the bedrock beneath your house, and keep going. It would sink through the Earth's crust like a stone through water, carving a narrow tunnel downward until it hit the core. And it would do this not because it's moving fast, because it's heavy, unimaginably, impossibly heavy for its size. That's what density means inside a white dwarf. That's the baseline, and it gets worse the deeper you go. The core of a white dwarf, where the pressure peaks, can reach densities 10 times higher, 10 million grams per cubic centimeter, 10,000 kilograms per sugar cube. At that point, the concept of weight stops meaning anything useful. You're not holding an object anymore. You're trying to contain a piece of a star using the physics of a planet, and the physics of a planet were never designed for this. The question that should be bothering you by now is how. How does matter even do this? How do atoms, which are mostly empty space, compress into densities 1,000,000 times greater than anything on Earth? The answer is that they don't, not as atoms, because at densities this extreme, atoms stop existing. The structure that gives matter its size, its chemical properties, its ability to form molecules and solids and everything you've ever touched, that structure gets obliterated. What replaces it is something stranger. An atom, under normal circumstances, is almost entirely empty space. If you could scale up a hydrogen atom to the size of a football field, the nucleus would be a pea sitting at the 50-yard line. The electron would be a speck of dust orbiting somewhere near the upper deck. The rest is nothing, empty space. Or more accurately, the probability field where the electron might be found if you looked for it. The electron doesn't orbit like a planet. It exists as a cloud of probability, a smear of possible locations surrounding the nucleus. The size of that cloud, the volume it occupies, is what gives the atom its size. And the thing keeping that cloud inflated, keeping it from collapsing into the nucleus, is the electromagnetic force. The electron is negatively charged. The nucleus is positively charged. They attract, but the electron is also moving in a quantum sense, and that motion keeps it from falling in. The atom is stable because the forces balance. Now take that atom and squeeze it, put it under pressure. At first, the atom resists. The electron cloud pushes back. The electromagnetic repulsion between neighboring atoms, between their overlapping electron clouds, provides resistance. This is what gives normal matter its incompressibility. You can't squeeze a rock into a smaller rock because the atoms are already as close together as they're willing to get. Press harder and the atoms push back harder. There's a limit, and that limit is set by the electron clouds refusing to overlap. But keep increasing the pressure. Increase it by a factor of 1,000,000, by a factor of 1,000,000,000. At some point, the electron clouds stop being able to resist. The pressure is so extreme that the electrons are forced out of their normal orbits entirely. They're squeezed out of the atom like toothpaste from a tube, stripped away from the nucleus, and compressed into the spaces between the nuclei. What you're left with is no longer an atom. It's a nucleus, a tiny kernel of protons and neutrons, surrounded not by its own private electron cloud, but by a sea of free electrons that belong to no particular nucleus and are shared by all of them. The material is no longer atomic, it's ionic, a plasma of bare nuclei swimming in an ocean of detached electrons. This is what happens inside a white dwarf. The pressure is so high that normal atomic structure cannot survive. The atoms are crushed, the electrons are ripped free. And the resulting state of matter, this mixture of ions and free electrons, is called degenerate matter. The name is a holdover from quantum mechanics. It doesn't mean the matter is morally corrupt or broken. It means the electrons have been forced into a state where the normal rules of atomic physics no longer apply. Under normal conditions, electrons in an atom occupy discrete energy levels. Ground state, first excited state, second excited state. Each level can hold a limited number of electrons, and the electrons fill the levels from the bottom up, following a set of rules laid out by quantum mechanics. This is what gives elements their chemical properties. This is why carbon behaves differently from oxygen. The arrangement of electrons determines how atoms bond, how they react, how they interact with light. It's the foundation of chemistry. Inside a white dwarf, that foundation is gone. The electrons are no longer bound to individual nuclei. They're free, and they're packed so tightly together that they fill every available low-energy state. There's no room left at the bottom. New electrons arriving have no choice but to occupy higher and higher energy levels, stacking up like passengers in an overcrowded elevator. The pressure that results from this stacking is called degeneracy pressure, and it has nothing to do with heat. It has nothing to do with motion. It is purely a consequence of quantum mechanics saying that two electrons cannot occupy the same state. They resist being compressed further, not because they're pushing against each other with some kind of force you can measure. They resist because the rules of the universe forbid them from overlapping. That resistance is what holds up a white dwarf. Not heat, not fusion, not any kind of thermal pressure. Just the quantum refusal of electrons to be squashed into the same space. It sounds absurd. It sounds like the kind of thing that shouldn't be strong enough to matter. And yet here we are, staring at objects the mass of the sun, compressed into the size of the Earth, held up by nothing but the stubbornness of electrons refusing to share a quantum state. The density required to reach this state is not subtle. You don't get degenerate matter by squeezing a little harder. You get it by applying pressures that would make the center of the Earth look like a gentle hug. The pressure at the core of the Earth is about 360 gigapascals. That's enough to compress iron into exotic crystal structures that don't exist anywhere on the surface. The pressure at the core of a white dwarf is about 1 billion gigapascals, 1 billion, 3 million times higher than the core of the Earth. At that pressure, the concept of a solid as you understand it stops making sense. The nuclei are packed so closely together that they're almost touching. Almost, but not quite, because even under these conditions, there's still a thin buffer of degenerate electrons between them, preventing direct contact. The electrons are compressed into the smallest possible volume, filling the gaps, providing just enough outward pressure to keep the nuclei from crashing into each other. The spacing between nuclei in a white dwarf is roughly 1/100th the size of a normal atom. Take a hydrogen atom, about 1 angstrom across. Inside a white dwarf, the nuclei are separated by about 1/100th of an angstrom. That's close enough that if you could somehow see them, the nuclei would look like they're almost touching, sitting in a crystalline lattice with electrons flowing through the gaps like a liquid. Except it's not a liquid, it's not a solid. It's a quantum fluid, a degenerate electron gas that behaves according to rules that have no everyday analog. You can't pour it, you can't freeze it, you can't melt it. It just is, sitting in a state that only exists under the most extreme conditions the universe allows, without collapsing all the way into a neutron star or a black hole. And the nuclei themselves, the bare ions sitting in that lattice, are not idle, they're vibrating, thermal motion. Even though the temperature inside a white dwarf's core can be millions of degrees, that heat doesn't contribute to the pressure. It doesn't hold the star up. The nuclei jitter and shake, but they're trapped in place by the sheer density of the surrounding material. They can't move past each other. They can't flow. They're locked into a grid, vibrating like atoms in a solid, even though the material around them is a quantum fluid. The result is a state of matter that has properties of both a solid and a plasma, depending on which part you're looking at. The nuclei are solid, the electrons are fluid, and the whole thing is held together not by chemical bonds, not by electromagnetic forces, but by gravity pressing down from above and degeneracy pressure pushing up from below. The transition from normal matter to degenerate matter doesn't happen suddenly. It's a gradient. Near the surface of a white dwarf, where the pressure is lower, the material is still a normal ionized plasma. Electrons are free, but not degenerate. They're moving fast, heated by the residual thermal energy from the collapse. You could describe that material using the same physics that describes the interior of the Sun. But go deeper. A few kilometers down, the pressure climbs. The electrons start to pile up in higher energy states. The degeneracy sets in. By the time you reach the core, tens of kilometers below the surface, the material is fully degenerate. The electrons have been compressed into the tightest possible configuration. The nuclei have arranged themselves into a crystalline lattice, and the pressure is so extreme that even quantum mechanics is starting to struggle to push back. This is where intuition fails completely. You might think that if you keep adding mass to a white dwarf, it would get bigger. More mass, more volume, same way a pile of sand gets larger when you add more sand. White dwarfs do the opposite. Add more mass and the white dwarf shrinks. The reason is gravity. More mass means stronger gravity. Stronger gravity means more compression. More compression means the degenerate electrons are forced into even higher energy states, packed even tighter, and the whole structure contracts. The relationship is inverse. A white dwarf with 6/10 the mass of the Sun has a radius of about 7,000 kilometers. A white dwarf with 1 solar mass has a radius of about 5,000 kilometers. More mass, smaller size. Keep going, and the trend continues. A white dwarf with 1.3 solar masses has a radius of about 3,500 kilometers. The densest white dwarfs are also the smallest. The surface gravity follows the same pattern. More mass, smaller radius, stronger gravity. A white dwarf with 6/10 of a solar mass has a surface gravity of about 100,000 times Earth's. A white dwarf at 1.3 solar masses has a surface gravity closer to 350,000 times Earth's. If you weigh 70 kilograms on Earth, you would weigh 7 million kilograms on the lighter white dwarf. On the heavier one, you'd weigh closer to 25 million kilograms. The difference between those two numbers is the difference between being flattened into a thin layer of atoms and being flattened into an even thinner layer of atoms. Either way, you're not walking away. The escape velocity from a white dwarf's surface is typically around 5,000 kilometers per second. That's about 1.5% the speed of light. For comparison, the escape velocity from Earth is about 11 kilometers per second. From the Sun, it's about 600 kilometers per second. A white dwarf requires 10 times the escape velocity of the Sun despite being a fraction of the size. The reason is density. Escape velocity depends on both mass and radius. Pack more mass into a smaller radius and the escape velocity skyrockets. At 5,000 kilometers per second, nothing built by humans could escape a white dwarf's gravity. No rocket, no probe, no spacecraft. If you landed on the surface, you'd be there forever, or at least until the material you're made of was crushed flat and absorbed into the surface. Light itself struggles to escape. Photons climbing out of the gravity well lose energy. The process is called gravitational redshift. A photon emitted from the core of a white dwarf with a certain wavelength, say ultraviolet, will have a longer wavelength by the time it reaches the surface. Some of the photon's energy is spent fighting gravity. The wavelength stretches, the light reddens. This is measurable. Astronomers can observe the spectrum of a white dwarf and see the telltale shift in wavelength that indicates how strong the gravitational field is. The stronger the field, the larger the redshift. For a typical white dwarf, the shift is small but detectable. For a white dwarf near the Chandrasekhar limit, the shift is large enough to move spectral lines noticeably. It's one of the ways astronomers measure the mass of a white dwarf from a distance. The material itself, this degenerate mixture of ions and electrons, has no analog on Earth. You can't make it in a lab. You can't simulate it except in computer models. The conditions required to produce it, the pressures and densities, are so far beyond anything achievable with human technology that the only places it exists are inside stellar remnants, white dwarfs, neutron star crusts, the cores of collapsing supergiants in the moments before they explode. That's it. If you want to study degenerate matter directly, you have to point a telescope at a dead star and work backward from the light it emits, piecing together the internal structure from models and observations and hoping the math holds up. The math does hold up. For decades, the theoretical predictions of how degenerate matter should behave under extreme conditions have matched the observations of real white dwarfs almost perfectly. The mass-radius relationship, the inverse correlation where more massive white dwarfs are smaller, was predicted by quantum mechanics before it was confirmed by observation. The cooling rates, the way white dwarfs fade over billions of years as they radiate away their residual heat, match the models to within a few percent. The crystallization of the core, the process where the ions lock into a lattice as the star cools, was predicted in the 1960s and confirmed by observations in the 2010s. The theory works. Degenerate matter behaves the way quantum mechanics says it should, and that's either comforting or unsettling depending on how much faith you put in equations that describe states of matter no human will ever touch. But there's a limit. There's always a limit. Degeneracy pressure is strong, but it's not infinite. The electrons can only be compressed so far before something else has to give. Add too much mass to a white dwarf, and the pressure climbs high enough that the electrons start running out of room. They're already occupying every available low-energy state. The only states left are higher and higher energy levels, and at some point, the energy of the electrons approaches the rest mass energy of a proton. When that happens, a new reaction becomes possible. Electrons and protons can merge. They combine to form neutrons, releasing a neutrino in the process. The neutrons don't obey the same exclusion rule as electrons. They can pack tighter. The star collapses further. The white dwarf phase ends. What comes next is either a neutron star or, if the collapse happens violently enough, an explosion. That boundary, the point where electron degeneracy pressure fails, is not theoretical. It's a hard limit. A line in the sand that no white dwarf can cross without ceasing to be a white dwarf. The universe doesn't allow exceptions. The limit was calculated in the 1930s by a physicist who saw the consequences before anyone else did. And understanding that limit, understanding why it exists and what happens when a white dwarf reaches it, requires digging into the quantum mechanics that makes degeneracy pressure possible in the first place. The math that explains how a cloud of electrons can hold up the mass of a star. The principle that says no two electrons can occupy the same state. The rule that, against all intuition, keeps dead stars from collapsing into oblivion. That's where the story turns. That's where the real strangeness begins. The problem with atoms is that they're liars. They present themselves as solid, dependable building blocks of reality. You look at a table and it looks solid. You touch it and it feels solid. You trust that the atoms making up that table are doing their job, holding together, maintaining structure, keeping the table from collapsing into a puddle of subatomic chaos. And under normal circumstances, the atoms do exactly that. But take those same atoms and subject them to the kind of pressure found inside a white dwarf, and they fold, they disintegrate. The electrons get ripped away from the nuclei. The structure that gave the atom its size, its chemical properties, its identity, disappears. What you're left with is a plasma of bare ions swimming in a sea of detached electrons. And the question that should be keeping you up at night is this: if the atoms are gone, if the normal structure of matter has been obliterated, what is holding the white dwarf up? Because something is. The white dwarf doesn't collapse into a neutron star. It doesn't collapse into a black hole. It sits there, stable, for trillions of years, defying gravity with no fusion, no heat, no conventional pressure pushing outward. The answer, when it finally came, arrived from a corner of physics so strange, so counterintuitive, that even the physicists who discovered it spent decades arguing about whether it was real. The answer came from quantum mechanics, and specifically from a single rule formulated by a young Austrian physicist named Wolfgang Pauli in 1925. A rule so simple you can state it in one sentence. A rule that holds up dead stars. The rule says that no two identical fermions can occupy the same quantum state. That's it. That's the whole thing. No two electrons in the same system can have the same position, the same momentum, the same spin, all at the same time. They refuse, not because of a force, not because they're pushing against each other. They refuse because the universe does not allow it. And that refusal, that quantum stubbornness, generates a pressure strong enough to prevent a star-sized mass from collapsing into oblivion. Let's back up. Because to understand why that rule matters, you need to understand what quantum mechanics is and why it behaves the way it does. Quantum mechanics is the set of rules that governs the behavior of particles at the smallest scales: atoms, electrons, photons. Anything smaller than you can see with your eyes, and most things smaller than you can see with a microscope. At those scales, the universe stops behaving the way your intuition says it should. Particles don't have definite positions until you measure them. They exist as clouds of probability smeared across space, occupying multiple locations at once until something forces them to pick. Light behaves like a wave and a particle depending on how you look at it. Energy comes in discrete chunks, packets called quanta, rather than smooth continuous values. The rules are strange, the math works. And whether or not the rules make sense to a human brain raised on a planet where things have definite locations and objects don't spontaneously tunnel through walls, the rules are what the universe runs on. Pauli's exclusion principle is one of those rules. It applies to a class of particles called fermions, named after the physicist Enrico Fermi. Electrons are fermions, Protons are fermions, neutrons are fermions. The defining feature of a fermion is a property called spin. Spin is not actually the particle spinning like a top. It's a quantum property that has no classical analog. But it behaves mathematically like angular momentum, and particles with half-integer spin, things like spin 1/2, are fermions. Particles with integer spin, like photons, are called bosons, and they don't obey the exclusion principle. Bosons are happy to pile into the same quantum state. That's how lasers work. Fermions are not. They refuse to share. The principle emerged from Pauli's attempts to explain why electrons in atoms occupy distinct energy levels. If you look at the periodic table, the structure of the elements, the way electrons fill up shells around the nucleus, there's a pattern. The first shell holds 2 electrons. The second shell holds 8. The third holds 18. The numbers aren't random, they're dictated by the exclusion principle. Each electron in an atom is described by a set of 4 quantum numbers: principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. Those 4 numbers define the electron's state. And Pauli's rule says that no 2 electrons in the same atom can have the same 4 numbers. If one electron occupies a state, that state is full. The next electron has to go somewhere else, into a higher energy level, a different orbital, a different configuration. The electrons stack up, filling the available states from the bottom up, and that stacking is what gives each element its unique properties. In a normal atom, this principle is what keeps the electrons from all collapsing into the lowest energy state, the ground state orbital closest to the nucleus. Electromagnetic attraction pulls the electrons toward the positively charged nucleus. The exclusion principle pushes back, forcing electrons into higher orbitals, spreading them out. The result is the familiar electron cloud structure, the shells and subshells, the reason chemistry works the way it does. Take away the exclusion principle and every electron in the universe would collapse into the ground state. Atoms would shrink to the size of their nuclei. Matter as we know it would cease to exist. Pauli formulated the principle in 1925 while trying to explain spectral lines, the specific wavelengths of light that atoms absorb and emit. He noticed that certain transitions between energy levels never happened. Electrons didn't jump into states that were already occupied. He wrote down the rule, published it, and within a few years it became one of the foundational principles of quantum mechanics. In 1940, the principle was extended by the spin statistics theorem, which proved that it applies to all fermions, not just electrons. The proof involved some of the deepest math in quantum field theory, but the upshot was simple. Fermions cannot overlap, ever, under any circumstances. The universe forbids it. Now take that rule and scale it up, not to an atom, to a star, to a white dwarf, to a place where a solar mass worth of matter has been compressed into a volume the size of Earth, and the pressure is so extreme that the atoms have been torn apart. The electrons are no longer bound to individual nuclei. They're free, floating in a plasma, shared by all the ions in the star. And they're packed so tightly together that every available low-energy state is full, completely full. There's no room left at the bottom. New electrons arriving, or existing electrons being compressed further, have no choice but to occupy higher energy states. They stack up, level after level, filling every possible configuration, because the exclusion principle won't let them double up. And the energy required to compress them into higher and higher states generates a pressure, a quantum mechanical pressure, degeneracy pressure. This is not a pressure in the way you normally think of pressure. It's not atoms bouncing off each other. It's not heat causing particles to move faster. It's not even a force in the traditional sense. It's a consequence of geometry in quantum state space. Imagine a parking lot with a finite number of spaces. Each space can hold one car. The exclusion principle says 2 cars can't occupy the same space. Fill up all the ground level spaces, and the next car has to park on the second level. Fill that up, and the next car goes to the third level. The higher you go, the more energy it costs to park there, because you have to drive up ramps, fight gravity, expend effort. In a white dwarf, the electrons are the cars. The quantum states are the parking spaces. Gravity is trying to compress all the electrons into the ground level. The exclusion principle says no. The electrons are forced into higher and higher energy states, and the energy cost of that compression is what generates the outward pressure that holds the star up. The formal name is electron degeneracy pressure. Degenerate in this context doesn't mean broken or corrupted. It's a technical term borrowed from quantum mechanics that refers to a state where particles are packed into the lowest available energy levels with no room left to compress further without violating the exclusion principle. The matter is degenerate because the electrons have run out of low energy states. They're jammed into the tightest possible configuration, and any attempt to squeeze them further requires pushing them into states with higher momentum, higher energy, and that requires doing work against the exclusion principle. That work shows up as pressure. Here's what makes this pressure strange. It doesn't depend on temperature at all. You can cool a white dwarf down to near absolute zero, and the degeneracy pressure doesn't change. You can heat it up to millions of degrees, and the degeneracy pressure still doesn't care. The pressure comes purely from the density, from how tightly the electrons are packed, not from how fast they're moving. In a normal gas, pressure increases with temperature. Heat the gas, and the particles move faster. Faster particles hit the walls of their container more often and with more force. Pressure goes up. Cool the gas, and the particles slow down. Pressure drops. In a degenerate gas, that relationship breaks. The electrons are already occupying every available state. Temperature just jiggles them around within those states. It doesn't change the fundamental fact that they're packed as tightly as the exclusion principle allows. The pressure is there whether the electrons are hot or cold. It's a quantum traffic jam, and traffic jams don't care about the weather. This is what allows white dwarfs to cool for trillions of years without collapsing. A normal star, one held up by thermal pressure from nuclear fusion, would collapse the moment the fusion stopped and the core cooled. No heat, no pressure, no support. Gravity wins. White dwarfs don't work that way. They're held up by degeneracy pressure, which is insensitive to temperature. The star can cool from 10 million degrees down to 10,000 degrees, and the core doesn't budge. The degeneracy pressure is still there, still pushing outward, still balancing gravity. The white dwarf just gets dimmer and dimmer as it radiates away its residual heat. Eventually it'll fade to black, but it won't collapse, not unless you add more mass. The discovery that degeneracy pressure could support a stellar remnant came in the late 1920s, just a few years after Pauli formulated the exclusion principle. Ralph Fowler, a British physicist, was the first to realize that the strange quantum rules governing electrons in atoms could also apply to the crushed cores of dead stars. In 1926, he published a paper showing that the pressure inside a white dwarf came not from heat, but from the quantum mechanical behavior of degenerate electrons. The paper solved a problem that had been bothering astronomers since the discovery of Sirius B. How could an object that dense, that small, that clearly not fusing anything, stay stable? Fowler's answer was quantum mechanics. The star was held up by a pressure that had no classical analog. a pressure that emerged purely from the Pauli exclusion principle, refusing to let electrons overlap. Fowler's model worked. It explained the mass-radius relationship of white dwarfs, the inverse correlation where more massive white dwarfs are smaller. The more mass you add, the stronger the gravity, the tighter the compression, the higher the energy states the electrons are forced into. The star shrinks. The model predicted that relationship before it was observationally confirmed. It also explained why white dwarfs didn't collapse further. Degeneracy pressure was enough. Barely, but enough. The star reached an equilibrium where the inward pull of gravity exactly balanced the outward push of the degenerate electron gas. The core stopped shrinking. It stabilized, and it could stay that way indefinitely. But there was a catch. Fowler's model assumed the electrons were moving slowly compared to the speed of light. That's a reasonable assumption for low-mass white dwarfs, where the densities, while extreme by everyday standards, aren't extreme enough to accelerate electrons to relativistic speeds. But add more mass, make the white dwarf heavier, the density climbs. The electrons get squeezed into higher energy states. Higher energy means higher momentum. Higher momentum means higher velocity. And at some point, the velocities approach the speed of light. When that happens, Fowler's equations break down. You need to account for special relativity. You need to correct for the fact that as particles approach light speed, their energy increases faster than their momentum. The pressure doesn't scale the same way. And when a young Indian physicist named Subramanian Chandrasekhar worked through the relativistic corrections in 1930, he found something unsettling. There was a limit. Chandrasekhar was 20 years old, fresh out of graduate school, sailing from India to England to begin a fellowship at Cambridge. He spent the voyage working through the math, calculating what happens to degeneracy pressure when the electrons inside a white dwarf are moving at speeds close to light. The result was a hard upper limit on the mass of a white dwarf. Beyond a certain mass, roughly 1.4 times the mass of the Sun, electron degeneracy pressure fails. The electrons run out of states. The exclusion principle can no longer generate enough pressure to hold the star up. Gravity wins. The star collapses. The number is now called the Chandrasekhar limit, and it sits at about 1.44 solar masses, though it's often rounded to 1.4. The exact value depends on the composition of the white dwarf, the ratio of protons to neutrons in the nuclei. But for a typical carbon-oxygen white dwarf, the limit is 1.44. Any white dwarf more massive than that cannot exist, not stably, not for long. The core will collapse, either into a neutron star if the collapse is gradual, or into a supernova if the collapse is sudden and violent. The universe does not allow exceptions. The limit is absolute. Chandrasekhar presented his result to the Royal Astronomical Society in 1935, expecting it to be received as a straightforward application of quantum mechanics and relativity to stellar structure. Instead, he was publicly ridiculed by Arthur Eddington, one of the most prominent astrophysicists of the era. Eddington refused to believe that stars could collapse indefinitely. He thought there had to be some other mechanism, some unknown pressure that would step in and prevent total collapse. He called Chandrasekhar's conclusion absurd. He mocked it in front of the entire astronomical community. Chandrasekhar, a young foreign scientist with no institutional power, was humiliated. He spent the next several years defending his work, refining the calculations, proving over and over that the math was correct. Eddington never accepted it. He died in 1944, still believing Chandrasekhar was wrong. History sided with Chandrasekhar. The limit was confirmed by observation. White dwarfs were found with masses clustering around 6/10 of a solar mass, well below the limit. No stable white dwarf was ever found above 1.4 solar masses. Supernovae, particularly Type 1I supernovae, were eventually understood to be white dwarfs that had accreted mass from a companion star until they crossed the Chandrasekhar limit and exploded. The limit was real. It was written into the fabric of the universe. And in 1983, 53 years after he first calculated it, Chandrasekhar was awarded the Nobel Prize in Physics. Eddington's name is still remembered, mostly for being brilliantly wrong about this one thing. The reason the limit exists is that degeneracy pressure, for all its quantum strangeness, is not infinite. The exclusion principle can only push back so hard. At low densities, the electrons occupy non-relativistic states. Their velocities are small compared to the speed of light. The pressure they generate scales with density to the 5/3 power. Add more mass, increase the density, and the pressure goes up faster than the gravitational pull. The star shrinks but stabilizes. At higher densities, the electrons are forced into relativistic states. Their velocities approach light speed. The pressure-density relationship changes. It scales with density to the 4/3 power. That's weaker. Gravity scales with density squared. At some point, the curves cross. Gravity pulls harder than degeneracy pressure can push. The equilibrium breaks. The star collapses. The Chandrasekhar limit is not a property of the star. It's a property of the universe. It's a consequence of combining the Pauli exclusion principle with special relativity and working through the math. Any white dwarf, anywhere, made of any material, will collapse if its mass exceeds roughly 1.4 solar masses. The number doesn't change. The physics doesn't bend. You can't engineer around it. You can't add supports. You can't reinforce the structure. The limit is built into the equations that govern how matter behaves under extreme conditions. Cross it, and the star is done being a white dwarf. What happens next depends on how fast the collapse occurs and whether there's anything left to stop it before it hits neutron star densities or below. The exclusion principle, Pauli's simple rule that no two fermions can occupy the same quantum state, is what makes white dwarfs possible. Without it, dead stars would collapse immediately. Gravity would compress them past the point of no return, straight into neutron stars or black holes, and there would be no stable intermediate stage. The universe would be missing an entire class of objects. Stars like the Sun, after exhausting their fuel, would have nowhere to go. They couldn't explode. They don't have enough mass. They couldn't collapse into neutron stars. The densities required are too high without something catastrophic triggering the collapse. They would just implode into some kind of undefined quantum sludge, and the models would break. But the exclusion principle exists. Electrons refuse to overlap. Degeneracy pressure pushes back, and white dwarfs are stable, sitting quietly in the dark, held up by nothing but the stubbornness of quantum mechanics. Think about what that means. Every white dwarf in the galaxy, every cooling ember sitting at the center of a faded planetary nebula, every Sirius B orbiting a bright companion, every faint point of light that used to be a star is being held up by a principle formulated in 1925 by a physicist trying to explain spectral lines in hydrogen. The principle wasn't discovered by studying white dwarfs, it was discovered by studying atoms. The fact that it scales up, that it works at densities 1,000,000 times higher than anything on Earth, that it holds up objects with the mass of the Sun compressed into the size of a planet, is one of the most remarkable confirmations of quantum mechanics ever observed. The theory says degeneracy pressure should exist. The stars exist. The pressure is real. The math works. And a dead star cooling in space doesn't care whether you find the explanation intuitive. It just sits there, balanced on a quantum rule, ticking down the eons. The white dwarf is stable now. The collapse has stopped. The atoms are gone, replaced by a degenerate plasma of ions and electrons locked in a quantum standoff with gravity. The core is still hot, millions of degrees, glowing from the heat of the collapse. But there's no fuel left, no fusion to replace the energy radiating into space. The star is an ember, and like any ember, it will cool, slowly, inevitably, over a timescale so long that the universe itself hasn't existed long enough for the process to finish. That cooling, that long fade into darkness, is its own story, and it's where the white dwarf's final act begins. The white dwarf is stable now. The collapse has stopped. The atoms are gone, replaced by a degenerate plasma of ions and electrons locked in a quantum standoff with gravity. The core is still hot, millions of degrees, glowing from the heat of the collapse, but there's no fuel left. No fusion to replace the energy radiating into space. The star is an ember, and like any ember, it will cool, slowly, inevitably, over a timescale so long that the universe itself hasn't existed long enough for the process to finish. That cooling, that long fade into darkness, is its own story, and it's where the white dwarf's final act begins. Here's the strange part. A white dwarf is not a star anymore. Not in the way you normally think of stars. Stars burn. They fuse hydrogen into helium, helium into carbon, climbing the periodic table one nuclear reaction at a time, releasing energy, radiating light, holding themselves up with the outward pressure of fusion. That's what makes a star, the fusion, the burning, the constant conversion of mass into energy that keeps the core hot and the structure inflated. A white dwarf does none of that. The fusion stopped long ago. The hydrogen is gone, the helium is gone. What's left is a ball of carbon and oxygen, compressed to 1,000,000 times the density of Earth, sitting in space with no internal energy source. It's not burning, it's not fusing, it's just cooling, and yet it glows. For billions of years it glows. Bright enough to be seen across thousands of light years. Hot enough to ionize the gas around it and light up the planetary nebula it left behind. The surface temperature of a freshly formed white dwarf sits around 100,000 degrees Kelvin. That's hotter than any star's surface except the most massive blue giants. The core temperature can reach 100 million degrees or more. For something with no fusion, no internal heat source, that's absurdly hot. The question is where that heat came from, and the answer is simple: gravity. When the core of the star collapsed, when the atoms were crushed and the electrons were squeezed into a degenerate state, all that gravitational energy had to go somewhere. It went into heat. The collapse compressed the material so violently that the kinetic energy of the infalling matter was converted into thermal energy. The core heated up, not because anything was burning, because it was crushed. That heat is what's left over. Residual thermal energy from the collapse, trapped in the ions and electrons, radiating outward into space at a rate determined purely by the surface area and the temperature gradient. The white dwarf is a cooling object, not a burning one. It's a hot rock in space, and rocks cool down. The problem is that cooling a white dwarf takes an unimaginable amount of time. You can't just wait a few million years and check back. You can't even wait a few billion years. The timescale is measured in trillions, with a T. Trillions of years for the white dwarf to cool from 100,000 degrees to 10,000. Trillions more to drop from 10,000 to a few thousand. And even at a few thousand degrees, the white dwarf is still radiating, still glowing faintly in the infrared, still technically alive in the sense that it's emitting energy and can be detected with sensitive instruments. The universe is 13.8 billion years old. That's not nearly long enough for any white dwarf to finish cooling. Let that sink in. Every white dwarf that has ever formed, from the moment the first low-mass stars ran out of fuel billions of years ago, is still cooling. None of them have finished. None of them have reached the end of the process. We have observed white dwarfs that have been cooling for 10 billion years, 12 billion years, maybe longer, and every single one of them is still warm, still radiating, still somewhere on the long downward slope of its cooling curve. The oldest white dwarfs we've found have surface temperatures of a few thousand degrees Kelvin, still hot enough to glow faintly in red and infrared light, still detectable, still ticking down the clock. The universe has not existed long enough for a white dwarf to go cold. The cooling process is straightforward in principle. The white dwarf has a reservoir of thermal energy stored in the motion of its ions and the kinetic energy of its degenerate electrons. That energy radiates away from the surface as light, mostly ultraviolet and visible light at first, then shifting toward red and infrared as the surface cools. The rate of cooling depends on the surface area and the temperature. Hotter objects radiate faster. Stefan Boltzmann law. The power radiated scales with the fourth power of the temperature. Double the temperature and the object radiates 16 times as much power. Cool the object down and the power drops rapidly. A white dwarf at 100,000 degrees radiates furiously. A white dwarf at 10,000 degrees radiates much more slowly. A white dwarf at 1,000 degrees is barely radiating at all, putting out less energy than a small star like Proxima Centauri. The early cooling phase is relatively fast. Relatively. A white dwarf starting at 100,000 degrees will cool to about 50,000 degrees in roughly 10 million years. Still hot, still bright, but noticeably cooler than when it started. Drop it to 25,000 degrees and you're looking at another 100 million years. The cooling is decelerating. Each successive halving of the temperature takes longer than the last. By the time the white dwarf reaches 10,000 degrees, billions of years have passed. By the time it drops to 5,000 degrees, you're talking about 10 billion years or more, and it keeps going, slower and slower. The temperature asymptotically approaches zero, but never actually gets there. Not in any time frame that matters. The first person to work through the math in detail was a British astrophysicist named Leon Mestel in 1952. Mestel calculated how long it would take for a white dwarf to cool by measuring the rate at which thermal energy escapes from the surface and comparing it to the total energy stored in the interior. His models showed that white dwarfs cool on timescales of billions to tens of billions of years, far longer than the age of the universe at the time. The prediction was testable. If white dwarfs really cooled that slowly, then the oldest white dwarfs in the galaxy should still be warm. Astronomers looked. They found white dwarfs with surface temperatures of 5,000 degrees, 7,000 degrees, 10,000 degrees, all of them billions of years old. All of them still glowing. Mestel's model held up. The cooling times were real. White dwarfs have become cosmic clocks because of this. If you can measure the surface temperature of a white dwarf, you can estimate how long it's been cooling. If you know when the white dwarf formed, you can use its current temperature to date the star cluster or galaxy it belongs to. The technique is called white dwarf cosmochronology, and it's one of the most reliable methods astronomers have for determining the ages of old stellar populations. Find the coolest white dwarfs in a cluster, and you've found the ones that have been cooling the longest. Those are the oldest. The progenitor stars that formed them were the first to die, which means they were the most massive stars in the cluster's original population. Work backward from the cooling time, and you can figure out when the cluster formed. The method has been used to date globular clusters, the thick disk of the Milky Way, even the age of the galaxy itself. The coolest white dwarfs we've found are about 12 billion years old. That puts a lower limit on the age of the Milky Way. The galaxy has to be at least as old as its oldest white dwarfs. The cooling process is not perfectly smooth. There are bumps, complications. One of the biggest is crystallization. As the white dwarf cools, the ions in the core, the bare carbon and oxygen nuclei sitting in a lattice, begin to slow down. At high temperatures, they're jittering and vibrating with thermal energy, moving around within the lattice like atoms in a hot solid. As the temperature drops, the thermal motion decreases. The ions vibrate less. They settle into more stable configurations. And at a certain temperature, about 6 million degrees Kelvin, the ions lock into place. They stop moving. The core crystallizes. Think about what that means. The core of a white dwarf is mostly carbon and oxygen. Carbon atoms and oxygen atoms, stripped of their electrons, packed into a dense plasma. As the plasma cools, the ions arrange themselves into a regular geometric pattern, a lattice, a crystal. The same structure you see in a diamond on Earth, where carbon atoms are locked into a face-centered cubic arrangement, is forming inside the core of a dead star. Except this diamond is the size of a planet. The entire core, thousands of kilometers across, solidifying into a single crystalline structure, a cosmic diamond, the largest diamond in the universe. And it's not metaphorical, it's literal. The carbon nuclei are bonding into the same lattice structure that makes diamonds on Earth. The physics is identical, the scale is not. The process was predicted in the 1960s by theorists working on the properties of dense matter. They realized that as the temperature dropped and the thermal energy of the ions decreased, the electrostatic repulsion between the positively charged nuclei would force them into the most energetically favorable arrangement. That arrangement is a crystal. A regular repeating lattice where each ion sits at a fixed distance from its neighbors, minimizing the total energy of the system. The transition from liquid to solid, from a plasma to a crystal, happens gradually as the core cools from the inside out. The center crystallizes first, where the pressure and density are highest. The solid core grows outward over billions of years, spreading through the interior like ice forming on a pond. Eventually, the entire core is crystallized. A solid ball of carbon and oxygen, locked into a lattice, surrounded by a thin outer layer of still liquid degenerate matter. The crystallization process releases energy, latent heat, the same phenomenon you see when water freezes into ice. The phase transition from liquid to solid releases a small amount of thermal energy that was stored in the disordered state. That energy heats the surrounding material and slows the cooling process. For a white dwarf, the latent heat released during crystallization can extend the cooling time by about 1 to 2 billion years. Not much compared to the trillions of years the whole process takes, but enough to be measurable. Astronomers have observed white dwarfs that are cooling more slowly than the models predict, and the leading explanation is crystallization. The cores are solidifying, releasing heat and keeping the stars warmer for longer than they would be otherwise. The data matches the theory. The cores are crystallizing, the diamonds are real. In 2024, astronomers using data from the Gaia Space Telescope confirmed that certain white dwarfs were sitting on what they called a cooling plateau, a range of temperatures where the white dwarfs seemed to stall out, cooling much more slowly than expected. The plateau lasted for billions of years. Some of the white dwarfs appeared to have stopped cooling entirely for 8 billion years or more before resuming their descent. The explanation, after ruling out other possibilities, was crystallization. The latent heat released during the phase transition was enough to pause the cooling for billions of years. The white dwarfs weren't defying thermodynamics, they were just taking their time. The heat had to go somewhere, and it was being radiated away as slowly as the laws of physics allowed. One white dwarf in particular has captured the public imagination, BPM 37093, also known as V886 Centauri. It's a white dwarf about 50 light-years from Earth, sitting in the constellation Centaurus. Its mass is about 1.1 solar masses, slightly above average for a white dwarf. The core is estimated to be about 90% crystallized. Astronomers have calculated, based on the mass and the cooling time, that the interior contains roughly 10 billion trillion carats of diamond. That number is meaningless in practical terms. You can't mine it, you can't reach it. You can't even get close without being vaporized by the surface heat or crushed by the gravity. But the diamond is there. The carbon nuclei are locked into a lattice. The core is a single crystal, planet-sized, cooling in the dark, waiting for the universe to end. The surface of the white dwarf cools faster than the interior. Heat flows from the hot core outward to the cooler surface where it radiates into space. The temperature gradient drives the cooling. The surface might be at 10,000 degrees while the core is still at 1,000,000. Over billions of years, the gradient flattens, the core cools, the surface cools. The entire structure slowly equalizes, approaching a uniform temperature that drops lower and lower as the energy escapes. The process is governed by the same principles that cool a cup of coffee on a table. Heat flows from hot to cold. The rate of flow depends on the temperature difference and the thermal conductivity of the material. Degenerate matter has high thermal conductivity. Heat moves through it easily, carried by the degenerate electrons zipping through the lattice. That keeps the interior relatively well mixed. No sharp temperature jumps, just a smooth gradient from the hot core to the cooler surface. By the time the white dwarf has cooled to a few thousand degrees, it's barely visible. It's no longer emitting much light in the visible spectrum. Most of its radiation is in the infrared. If you pointed a regular optical telescope at it, you might not see anything. You'd need an infrared telescope, something like the James Webb Space Telescope, to pick up the faint glow. The white dwarf is still there, still radiating, still cooling, but it's fading into the background, blending into the darkness of space. Give it a few more trillion years and it'll drop below 1,000 degrees. At that point, it's emitting almost no light at all. Just a faint whisper of infrared radiation, barely distinguishable from the cosmic microwave background. It's still a white dwarf, still supported by electron degeneracy pressure, still sitting at 1,000,000 times the density of Earth, but it's cold and getting colder. The final stage of a white dwarf's life is called a black dwarf, a completely cooled white dwarf, no light, no heat. Just a lump of degenerate matter, a crystallized core of carbon and oxygen, sitting in space at the ambient temperature of the universe. A black dwarf is the end of the line, the final state of a low-mass star. No more changes, no more evolution, just a cold, dark, dense object, invisible except for its gravitational influence, a fossil, a tombstone, the last remnant of a star that died trillions of years ago. Here's the problem. Black dwarfs don't exist yet, not one. The universe is only 13.8 billion years old. That's not nearly long enough for any white dwarf to cool completely. The coolest white dwarfs we've observed, the ones that have been cooling for more than 10 billion years, are still radiating at a few thousand degrees, still warm, still glowing faintly. The cooling time required to reach true black dwarf status is somewhere between 10 trillion and 100 trillion years, depending on the mass and composition of the white dwarf. 10 trillion years. The universe would have to age another 700 times longer than it has already existed for the first black dwarfs to appear. And that's just the beginning. Some models predict that the very last white dwarfs, the ones with the lowest masses and the slowest cooling rates, won't finish cooling for 10 to the 38th years. That's a 1 followed by 38 zeros. A number so large it has no meaning in human terms. The age of the universe might as well be 0 compared to that. By the time black dwarfs start appearing, the universe will be unrecognizable. Star formation will have stopped. The gas clouds that fuel new stars will have been exhausted or dispersed. Galaxies will have merged, collided, or drifted apart as the expansion of the universe accelerates. The Milky Way, if it still exists, will be a graveyard. White dwarfs, neutron stars, black holes, and the occasional brown dwarf. That's it. No bright stars, no blue giants, no supernovae. Just the slowly cooling embers of stars that died trillions of years ago, fading one by one into invisibility. The black dwarfs will outnumber everything else, silent, invisible, waiting, and even then, they're not truly inert. Quantum mechanics has one more trick. Over timescales of 10 to the 32 years or longer, quantum tunneling may allow the protons in the black dwarf's core to decay into lighter particles. Proton decay is purely theoretical. It's never been observed. But some extensions of the standard model of particle physics predict it should happen eventually. If it does, the black dwarf won't stay a black dwarf. It'll slowly evaporate, losing mass one proton at a time, until there's nothing left but a diffuse cloud of radiation. That process takes so long that calling it slow is an insult to the word. 10 to the 40 years, 10 to the 100 years, numbers that make a trillion look like a blink. The white dwarf sits in the present, hot and bright, radiating the last traces of a collapse that happened billions of years ago. It's cooling, slowly, inevitably. The core is crystallizing, locking into a lattice that will outlast galaxies. The surface is fading, dropping through the spectrum from ultraviolet to visible to infrared to nothing. The clock is ticking, and the clock has trillions of years left on it. Trillions of years of slow, patient cooling, of heat leaking into the void, of photons carrying away the last remnants of a star's life. The white dwarf is stable, supported by degeneracy pressure, held up by the exclusion principle, but it's mortal, not in the sense that it'll collapse or explode, in the sense that it's dying, slowly, on a timescale that dwarfs the history of everything humans have ever known. The universe is young, absurdly young compared to the lifespan of a cooling white dwarf. We're living in the era of bright stars and active galaxies, a brief moment when fusion is still common and the sky is full of light. That era will end, the stars will burn out, the white dwarfs will take over, and for trillions upon trillions of years, the universe will be lit not by fusion, but by the fading glow of stellar corpses, cooling embers scattered across the dark, waiting for the heat death of everything. But the white dwarf's story has one more chapter before it fades completely. One more boundary to cross, one more limit that cannot be exceeded. Because as stable as a white dwarf is, as patient as its cooling process may be, there's a line it cannot cross, a mass it cannot exceed. Push a white dwarf past that line and the cooling stops, the stability breaks, and what happens next is not a slow fade into darkness, it's an explosion. There is a number, one number, sitting at the intersection of quantum mechanics, special relativity, and the coldest violence the universe has to offer. 1.4 solar masses. That's it. That's the line. Cross it and a white dwarf stops being a white dwarf. Not gradually. Not over billions of years. Immediately. The moment the mass climbs past that threshold, the rules change. Electron degeneracy pressure, the quantum stubbornness that has been holding the star up for eons, fails. The exclusion principle runs out of room. Gravity wins. And what happens next is either a catastrophic collapse into a neutron star or an explosion so bright it can outshine an entire galaxy. The number is called the Chandrasekhar limit, and the story of how it was discovered is one of the strangest episodes in the history of physics. A 20-year-old student, fresh out of graduate school, working through equations on a ship in the middle of the Indian Ocean, arriving at a conclusion so unsettling that the most respected astrophysicist of the era spent the rest of his life trying to prove it wrong. The student was right. The established expert was wrong, and it took 50 years for the scientific community to fully admit it. Subramanian Chandrasekhar was born in 1910 in Lahore, then part of British India, now in Pakistan. He was brilliant. Not the kind of brilliant that gets you into a good university. The kind of brilliant that makes professors uncomfortable because you're asking questions they don't have answers for. By the time he was 19, he had completed a bachelor's degree in physics at Presidency College in Madras, now Chennai. He had read Fowler's 1926 paper on white dwarfs, the one that explained how electron degeneracy pressure could support a stellar remnant, and he understood it better than most physicists twice his age. In 1930, he was awarded a scholarship to study at Cambridge University in England under Ralph Fowler himself. He boarded a ship in Bombay and spent the next 3 weeks crossing the Indian Ocean. Most people on a long voyage read novels or stare at the water. Chandrasekhar did math. He had brought papers with him, Fowler's work on white dwarfs, Sommerfeld's work on degenerate gases, Eddington's work on stellar structure, and he started thinking about what happens to a white dwarf if you make it heavier. Fowler's model assumed the electrons in a degenerate gas were moving slowly compared to the speed of light. That's a reasonable assumption for low-mass white dwarfs. But what if the white dwarf was more massive? What if the gravity was strong enough to compress the electrons so tightly that their velocities approached light speed? Fowler's equations wouldn't hold. You'd need to account for special relativity. Chandrasekhar decided to work through the relativistic corrections while he had time to kill on the ship. The math is not simple. You're starting with the equation of state for a degenerate electron gas, which relates pressure to density. Then you're correcting for the fact that as particles approach the speed of light, their energy increases faster than their momentum. The relationship between pressure and density changes. In the non-relativistic case, pressure scales with density to the 5/3 power. In the ultra-relativistic case, where the electrons are moving close to light speed, pressure scales with density to the 4/3 power. That's weaker. Gravity, meanwhile, scales with density squared. At low densities, degeneracy pressure wins. The star is stable. At high densities, the pressure doesn't climb fast enough to keep up with gravity. The curves cross. Equilibrium becomes impossible. Chandrasekhar worked through the algebra. He integrated the equations. He solved for the maximum mass a white dwarf could have before the pressure-gravity balance broke down. The answer came out to about 1.4 times the mass of the Sun. The exact number depends on the composition of the white dwarf, the ratio of protons to neutrons in the nuclei. But for a typical carbon-oxygen white dwarf, the value is close to 1.44 solar masses. Any white dwarf more massive than that cannot be stable. The math doesn't allow it. Electron degeneracy pressure is not strong enough to hold up the star. The core collapses. Chandrasekhar arrived at Cambridge in the fall of 1930 with a result that fundamentally altered the understanding of how stars die. He was 20 years old. He had done the calculation on a ship. He had no idea he was about to walk into a firestorm. The first person he showed the work to was Fowler. Fowler looked at the math, checked the derivation, and agreed it was correct. He encouraged Chandrasekhar to publish. Chandrasekhar wrote up the result and submitted it to the Astrophysical Journal in 1931. The paper was published without much fanfare. A few astronomers noticed, most didn't. The idea that white dwarfs had a mass limit was interesting, but it didn't seem to have immediate observational consequences. All the white dwarfs that had been measured at that point, including Sirius B, were well below the limit. Nobody had found a white dwarf anywhere near 1.4 solar masses. The limit was real in theory. It wasn't clear if it mattered in practice. Then Chandrasekhar kept working. Over the next few years, he refined the calculation. He extended the model to account for different compositions. He worked out what would happen to a star that exceeded the limit. The conclusion was unavoidable. If you added mass to a white dwarf and pushed it past 1.4 solar masses, the degeneracy pressure would fail. The star would collapse. Not into another white dwarf, into something denser, something smaller. At the time, neutron stars hadn't been discovered yet. Black holes were purely theoretical. Chandrasekhar didn't know what the endpoint was. He just knew the white dwarf phase couldn't continue. The star would keep collapsing until some other force stepped in to stop it, or it wouldn't stop at all. In January 1935, Chandrasekhar presented his results at a meeting of the Royal Astronomical Society in London. The title of his talk was "The Highly Collapsed Configurations of a Stellar Mass." He laid out the math. He explained the limit. He argued that stars above a certain mass could not end their lives as stable white dwarfs. They would collapse indefinitely. The audience listened. Then Arthur Eddington stood up. Eddington was not just any astronomer. He was the most famous astrophysicist in the world. He had led the 1919 solar eclipse expedition that confirmed Einstein's general theory of relativity. He had written textbooks on stellar structure. He was a knight, he was untouchable, and he thought Chandrasekhar was wrong. Not wrong in the sense that the math had an error, wrong in the sense that the conclusion was absurd. Eddington refused to believe that stars could collapse indefinitely. He believed there had to be some mechanism, some unknown pressure that would step in and prevent total collapse. He didn't know what that mechanism was. He just believed it had to exist, because the alternative, a star collapsing past the point of no return, was too strange to accept. Eddington delivered a rebuttal immediately after Chandrasekhar's talk. He mocked the conclusion. He called it a reductio ad absurdum. He said the mathematics might be correct, but the physical interpretation was nonsense. Stars don't just collapse. There has to be a way out. The fact that the equations predicted otherwise meant the equations were missing something. He didn't specify what. He just insisted Chandrasekhar had to be wrong. The audience sided with Eddington. Chandrasekhar, a young foreign scientist with no reputation, was publicly humiliated. He left the meeting devastated. Eddington's objection wasn't based on the math. It was based on intuition. He couldn't accept that the universe would allow a star to collapse without limit. He thought it violated some basic principle of nature. He spent the next several years publishing papers arguing against Chandrasekhar's result. None of them identified an actual error. None of them proposed an alternative mechanism that could hold up a white dwarf above the mass limit. They just insisted the limit couldn't be real. Eddington was wrong. Completely, fundamentally wrong. But he was famous. He had institutional power, and for years the astronomical community was too intimidated to contradict him. Chandrasekhar didn't give up. He kept refining the work. He published more papers. He extended the model to include rotation, magnetic fields, different compositions. Every calculation confirmed the same result. 1.4 solar masses. That's the limit. No exceptions. He moved to the University of Chicago in 1937 and spent the next 50 years there, working on a dozen different areas of astrophysics. But the Chandrasekhar limit remained the foundation of his career. He never stopped defending it. Eddington never accepted it. Eddington died in 1944, still convinced he was right. Chandrasekhar outlived him by 50 years. The observations eventually settled the question. As more white dwarfs were discovered and their masses measured, a clear pattern emerged. Every single one of them had a mass below 1.4 solar masses, not close to the limit, well below it. The typical white dwarf mass is about 6/10 of a solar mass. Some are heavier, some reach 1 solar mass or slightly above, but none have ever been found stably sitting above 1.4. The limit is real, the universe enforces it, and the reason is exactly what Chandrasekhar calculated in 1930 on a ship in the Indian Ocean. Electron degeneracy pressure has a maximum. Push past it and the star collapses. The physics behind the limit is not mysterious once you work through it. Degeneracy pressure comes from the Pauli exclusion principle. Electrons can't occupy the same quantum state. Pack them tightly enough and they're forced into higher and higher energy states. The energy required to compress them further generates an outward pressure. That pressure depends on how fast the electrons are moving. At low densities, the electrons are moving slowly, their momentum is small. The pressure scales nicely with density. Add more mass, increase the density, and the pressure climbs faster than gravity pulls. The star is stable, but as the density increases, the electrons are squeezed into higher momentum states. Their velocities increase. At some point, the velocities approach the speed of light. When that happens, the relationship between energy and momentum changes. In classical mechanics, kinetic energy is half the mass times the velocity squared. In special relativity, when velocities approach light speed, the energy grows much faster than the momentum. The electrons gain energy, but the pressure they generate doesn't keep up. The equation of state softens. Pressure no longer scales as strongly with density. And at a certain density corresponding to a certain mass, the pressure stops being able to balance gravity. The star can't hold itself up anymore. It collapses. The exact value of the limit depends on the composition of the white dwarf. Specifically, it depends on the ratio of electrons to nucleons, the protons and neutrons in the nuclei. For a pure helium white dwarf, where each nucleus has 2 protons and 2 neutrons and 2 electrons, the ratio is 1 electron per 2 nucleons. For a carbon-oxygen white dwarf, the ratio is slightly different. Carbon has 6 protons, 6 neutrons, 6 electrons. Oxygen has 8 protons, 8 neutrons, 8 electrons. The average ratio is close to 1 electron per 2 nucleons. That gives a limit of about 1.44 solar masses. If the white dwarf has a higher proportion of heavier elements, elements with more neutrons per proton, the ratio drops and the limit decreases slightly. If the white dwarf is spinning rapidly, rotation adds a small amount of extra support and the limit can be slightly higher. But these are minor corrections. For most purposes, the limit is 1.4 solar masses. That's the number astronomers use. That's the threshold. The fate of a white dwarf that exceeds the limit depends on how the mass is added. If the mass piles on slowly, the white dwarf contracts gradually. The core heats up as it compresses. At some point, the temperature and density climb high enough that a new reaction becomes possible: electron capture. Electrons and protons merge to form neutrons, releasing neutrinos. The neutrons don't obey the exclusion principle in the same way electrons do. They can pack tighter. The star collapses past white dwarf densities into neutron star densities. The collapse happens fast, seconds. The outer layers of the star implode. If there's enough material left, the implosion can trigger a supernova. If not, the star just collapses into a neutron star, and the outer envelope drifts away quietly. The other possibility is that the mass is added quickly. If a white dwarf is part of a binary system and its companion is a normal star shedding material, the white dwarf can accrete that material onto its surface. Hydrogen from the companion falls onto the white dwarf, piles up, heats up under the pressure, and eventually ignites. The fusion of hydrogen into helium releases energy. If the accretion rate is just right, the fusion happens steadily, and the white dwarf grows slowly over millions of years. If the rate is too high, the fusion becomes unstable. The temperature spikes, the reaction runs away. And if the white dwarf's mass climbs close enough to the Chandrasekhar limit while this is happening, the entire star can ignite all at once. Carbon fusion begins in the core. The core is degenerate, which means it doesn't expand when it heats up. The temperature skyrockets. The fusion rate explodes. Within seconds, the entire white dwarf is consumed in a runaway thermonuclear reaction. The star doesn't collapse. It explodes completely. The explosion is called a Type 1a supernova, and it's one of the brightest events in the universe. The Chandrasekhar limit is not just a number, it's a boundary, a line separating two fundamentally different kinds of objects. Below the limit, you have a white dwarf, a stable, cooling ember held up by electron degeneracy pressure, slowly fading over trillions of years. Above the limit, you have a catastrophe, either a collapsing core that becomes a neutron star or an exploding star that destroys itself entirely and seeds the surrounding space with heavy elements. The universe does not allow middle ground. You're either below the limit or you're not. There's no such thing as a white dwarf at 1.5 solar masses sitting quietly in space. It doesn't exist. It can't exist. The physics forbids it. The surprising thing is that all observed white dwarfs are well below the limit. The most massive white dwarf ever measured sits at about 1.35 solar masses. Close, but not over. Most are significantly lighter. The distribution peaks around 0.6 of a solar mass and drops off sharply above 1 solar mass. The reason is that the progenitor stars, the stars that become white dwarfs, shed a lot of mass during their red giant phase. A star that starts out with 5 solar masses might lose half its mass or more by the time it finishes puffing off its outer envelope. What's left, the core that becomes the white dwarf, is a fraction of the original mass. Only the most massive progenitor stars, those starting with 8 to 10 solar masses, can produce white dwarfs that approach the Chandrasekhar limit, and even those stars are rare. The galaxy is full of white dwarfs. Almost none of them are close to the edge. The limit also sets a threshold for the existence of neutron stars and black holes. If white dwarfs could be arbitrarily massive, there would be no need for denser objects. Every dead star would just settle into a white dwarf and cool off. The fact that there's a limit means some stars have to collapse further. Stars more massive than about 8 solar masses don't end as white dwarfs at all. Their cores get hot enough to fuse carbon, neon, oxygen, silicon. They keep climbing the periodic table until they hit iron. Iron doesn't fuse. The core collapses. The star explodes. What's left is either a neutron star or a black hole, depending on how much mass is left after the explosion. The Chandrasekhar limit is the dividing line. It's the reason the universe has neutron stars. It's the reason black holes exist. Without the limit, the stellar graveyard would be a lot simpler and a lot less interesting. The mathematical expression for the limit is not particularly complicated. Chandrasekhar worked it out in terms of fundamental constants: the speed of light, Planck's constant, the gravitational constant, the mass of a proton, the ratio of electrons to nucleons. Plug in the numbers and out comes 1.44 solar masses. The limit doesn't depend on anything arbitrary. It's not a parameter you can tune. It's baked into the structure of the universe. The same way the speed of light is the same everywhere, the Chandrasekhar limit is the same everywhere. A white dwarf in the Andromeda galaxy obeys the same rule as a white dwarf in the Milky Way. A white dwarf, forming 10 billion years ago, followed the same limit as one forming today. The physics doesn't change, the number doesn't drift. Chandrasekhar published more than 400 papers over his 50-year career. He wrote 10 books. He worked on stellar structure, radiative transfer, hydrodynamic stability, black holes, gravitational waves. He won the Nobel Prize in Physics in 1983, shared with William Fowler, for his work on the structure and evolution of stars. The prize came 53 years after he first calculated the limit, 53 years after Eddington publicly humiliated him, 53 years after the astronomical community dismissed his work as absurd. He was vindicated. The limit carries his name. Every astronomer in the world knows it. Eddington's objections are a footnote, a cautionary tale about what happens when intuition overrides mathematics. The limit is now one of the most important numbers in astrophysics. It's used to measure the masses of white dwarfs from their radii. It's used to model binary star evolution. It's used to predict when white dwarfs will explode as supernovae. It's used to date stellar populations by counting the number of white dwarfs that have cooled below detectable temperatures. The entire field of white dwarf cosmochronology rests on the assumption that the Chandrasekhar limit is correct. And every observation, every measurement, every supernova that matches the predicted brightness confirms that it is. The limit works, the math holds, the universe obeys. There are variations. The limit can shift slightly depending on the white dwarf's composition, its rotation rate, its magnetic field strength. A rapidly rotating white dwarf can support slightly more mass because the centrifugal force provides an extra outward push. A white dwarf with a strong magnetic field can be slightly more massive because the field pressure adds to the degeneracy pressure. But these effects are small, a few percent at most. The basic limit, 1.4 solar masses, is robust. It's the number that matters, the number that separates stability from catastrophe, the number that determines whether a star fades quietly over trillions of years or explodes in a burst of light visible across the universe. And that explosion, that runaway thermonuclear detonation that happens when a white dwarf crosses the line, is where the story turns violent. Because the Chandrasekhar limit isn't just a boundary for stability, it's a trigger, a countdown. The moment a white dwarf approaches that mass, either by accreting material from a companion star or by some other mechanism, the clock starts ticking, the core heats up, the pressure climbs, the carbon and oxygen nuclei, locked in their crystalline lattice, start to feel the squeeze, and at a certain point, the temperature crosses a threshold where carbon fusion can ignite. When it does, the white dwarf doesn't just collapse, it explodes, completely, violently. In a flash of light so bright it can be seen halfway across the universe. That explosion is the next chapter. And it's one of the most important events in the cosmos. The white dwarf is sitting in the dark. It has been cooling for billions of years, radiating away the last traces of heat from a collapse that happened when the galaxy was young. The surface temperature has dropped from 100,000 degrees to maybe 20,000. Still hot by any reasonable standard, but cooling, fading. Following the script every white dwarf follows. Slow decline over trillions of years until the universe forgets it exists. That's the plan. That's what should happen. Except this white dwarf isn't alone. There's another star in the system, a companion. Maybe a red giant, bloated and old, its outer atmosphere so loosely bound that material is drifting away into space like smoke from a dying fire. Maybe a main sequence star, still burning hydrogen, but close enough that its gravity is pulling the white dwarf into a tight orbit. Close enough that the distance between them is measured in fractions of an astronomical unit. Close enough that the white dwarf's gravity, 300,000 times stronger than Earth's at the surface, is reaching across the gap and pulling material off the companion. Gas, mostly hydrogen, streaming across the space between the two stars in a thin bridge of matter, spiraling down onto the white dwarf's surface like water circling a drain. This process is called mass transfer. It's common. Roughly half of all stars in the galaxy are in binary systems, orbiting each other, locked in gravitational dances that can last billions of years. When one of those stars dies and becomes a white dwarf, and the other star is still alive, still shedding material, the white dwarf becomes a vacuum cleaner. It pulls. The companion loses mass. The white dwarf gains mass, slowly. A few millionths of a solar mass per year. Not much, but it adds up. And every gram of matter that falls onto the white dwarf makes it heavier. Here's the problem. We just spent an entire chapter explaining that white dwarfs have a mass limit, 1.4 solar masses, the Chandrasekhar limit, the boundary where electron degeneracy pressure stops being strong enough to hold the star up. Cross that line, and the white dwarf either collapses into a neutron star or explodes. There is no third option. The universe does not allow stable white dwarfs above 1.4 solar masses. The math forbids it. The observations confirm it. Every white dwarf ever measured is below the limit, every single one. So when a white dwarf in a binary system starts accreting mass, when it starts pulling material off its companion and piling it onto its own surface, you're building toward an endpoint. You're running a countdown. The white dwarf might start at 6/10 of a solar mass, perfectly stable, perfectly safe. But add material for a few million years and it climbs to 7/10, then 8/10, then 1 solar mass. The white dwarf is getting heavier, and as it gets heavier, it shrinks. Remember, more mass means smaller radius. The gravity gets stronger, the core compresses, the density climbs, the temperature rises. The white dwarf is being squeezed tighter and tighter, not because anything is pushing on it from outside, but because its own gravity is pulling harder with every gram of added mass. At some point, the white dwarf crosses 1 solar mass, then 1.1, then 1.2. The pressure in the core is climbing. The degenerate electrons are being forced into higher and higher energy states. The carbon and oxygen nuclei, locked in their crystalline lattice, are vibrating faster as the temperature climbs. The core is still stable, still supported by degeneracy pressure, but the margin is shrinking. The white dwarf is approaching the edge. And the closer it gets, the hotter the core becomes. Here's where things get dangerous. Carbon is a fuel, so is oxygen. Under normal circumstances, they don't burn. The temperatures required to ignite carbon fusion are around 500 million degrees Kelvin. That's hotter than the core of the sun. The sun will never reach that temperature. It'll die as a white dwarf long before its core gets hot enough to fuse carbon. But a white dwarf that's accreting mass, a white dwarf climbing toward the Chandrasekhar limit, doesn't follow the same rules. The compression heats the core, slowly at first, then faster. By the time the white dwarf reaches 1.3 solar masses, the core temperature is approaching 1 billion degrees. That's still not hot enough for carbon fusion to ignite in any sustained way, but it's close, uncomfortably close. The white dwarf keeps accreting. 1.35 solar masses, 1.4. The core is now at 1 billion degrees, maybe higher. The density is around 10 to the 9 grams per cubic centimeter. 1 billion grams per cubic centimeter, 1 million times denser than the core of the Earth. The carbon nuclei are packed so tightly that they're almost touching, separated only by the thin buffer of degenerate electrons. The electrons are moving at close to the speed of light. The degeneracy pressure is maxed out. There is no more room. The white dwarf is at the limit, and the core is hot enough that carbon fusion can ignite. Under normal conditions, if you ignited carbon in a star's core, the core would heat up, expand, and cool back down. The expansion would reduce the pressure. The fusion rate would drop. The star would stabilize. This is how normal stars regulate themselves. Heat up, expand, cool off. It's a negative feedback loop. It keeps fusion under control. White dwarfs don't work that way. A white dwarf's core is degenerate. Degenerate matter doesn't expand when it heats up. The pressure depends on density, not temperature. Heat the core, and the pressure doesn't change. The core doesn't expand. The density stays the same. The temperature keeps climbing, and the fusion rate, which depends exponentially on temperature, explodes. This is called a thermonuclear runaway. Carbon fusion ignites somewhere in the core, maybe at the center where the temperature is highest, maybe slightly off-center, in a region where the density and temperature happen to hit the ignition threshold first. Doesn't matter. The moment fusion starts, it releases energy. The energy heats the surrounding material. The temperature rises, the fusion rate doubles, then doubles again, then again. Within a fraction of a second, the entire core is burning, not gradually, not in a controlled way, all at once. Every carbon nucleus within a radius of a few thousand kilometers fusing into heavier elements, releasing energy at a rate that makes the sun look like a candle. The energy release is staggering. A typical Type 1a supernova releases about 1 × 10⁴ joules within the first few seconds. That's 10⁴, a 1 followed by 44 zeros. For comparison, the Sun radiates about 3.8 × 10⁻26 joules per second. The supernova releases 10 to the 18 times more energy in a few seconds than the Sun radiates in an entire second. It's not just bright, it's violently, incomprehensibly bright. At peak brightness, a Type 1a supernova can outshine every star in its host galaxy combined. All 400 billion stars in the Milky Way, if you could see them all at once, would be dimmer than a single exploding white dwarf. The explosion doesn't just destroy the white dwarf, it obliterates it. The thermonuclear burning converts a significant fraction of the star's mass into heavier elements. Carbon fuses into neon, sodium, magnesium. Oxygen fuses into silicon, sulfur, phosphorus. Silicon fuses into iron, cobalt, nickel. The fusion runs so hot and so fast that it produces elements all the way up to the iron peak, the group of elements around iron that are the most stable nuclei in the universe. Roughly half a solar mass of iron group elements, mostly nickel-56, is synthesized in the explosion. Another half, solar mass or so, is blown apart without fusing, scattered into space as carbon and oxygen. the white dwarf that took billions of years to cool, that survived trillions of years of cosmic history, is gone in less than a second, completely. There's no remnant, no core left behind. No neutron star, no black hole, just an expanding cloud of gas and radiation moving outward at speeds of 10,000 to 20,000 kilometers per second, carrying the ashes of the explosion into the surrounding space. The light curve, the graph of how bright the supernova appears over time, is remarkably consistent. Type 1a supernovae follow a predictable pattern. The brightness climbs rapidly over the first 2 weeks as the expanding shell of debris heats up and becomes transparent. Peak brightness occurs about 17 to 19 days after the explosion. At that point, the supernova reaches an absolute visual magnitude of about -19.3. That's roughly 5 billion times brighter than the Sun. Hold that number for a second. 5 billion times brighter than the Sun. A single exploding white dwarf for a few weeks is putting out more light than 5 billion suns. If a Type 1a supernova went off in the nearest star system to Earth, Alpha Centauri, about 4 light-years away, it would appear in our sky as bright as the Sun. Not the Moon, the Sun. A second sun, blazing in the night sky, bright enough to cast shadows, bright enough to read by, visible in broad daylight, and it would stay that bright for weeks. After peak brightness, the light curve declines, slowly at first, then faster. The decline is powered by the radioactive decay of nickel-56, one of the primary fusion products synthesized in the explosion. Nickel-56 has a half-life of about 6 days. It decays into cobalt-56, which has a half-life of about 77 days. Cobalt-56 decays into stable iron-56. Each decay releases gamma rays, which heat the expanding debris and keep it glowing. The light curve follows the decay rate almost exactly. The supernova fades by about 1 magnitude every 50 days or so, tracking the half-life of cobalt-56. By 3 months after the explosion, the supernova has faded to about 1% of its peak brightness. By a year, it's down to less than 1,000th. Eventually, the debris cools, the radioactive isotopes decay completely, and the remnant becomes invisible. But for those first few weeks, the supernova is one of the brightest objects in the universe. The uniformity of Type 1a supernovae is what makes them useful. Not just interesting, useful. Almost every Type 1a supernova reaches the same peak brightness, absolute magnitude -19.3, give or take a few tenths of a magnitude. The reason is that they all come from the same progenitor, a carbon-oxygen white dwarf at the Chandrasekhar limit. 1.4 solar masses, same mass, same composition, same core conditions. The explosion is triggered the same way every time. Carbon ignition in a degenerate core, thermonuclear runaway, complete disruption. The physics is identical. The energy release is identical. The peak brightness is identical. And if you know how bright an object actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. Basic inverse square law. Brightness falls off with the square of the distance. Double the distance and the brightness drops by a factor of 4. Measure the apparent brightness and the intrinsic brightness, and you can solve for the distance. Type Ia supernovae, because they're so bright and so uniform, can be seen across enormous distances and used as standard candles to measure the scale of the universe. The term standard candle comes from an analogy. Imagine you're standing in a dark field at night and you see a candle in the distance. If you know the candle has a certain intrinsic brightness, say it's a standard candle that always puts out the same amount of light, You can estimate how far away it is by measuring how dim it appears. Bright candle looks dim, must be far away. Dim candle, close up, simple. In astronomy, standard candles are objects with known intrinsic brightness that can be used to measure distances. Cepheid variables, the pulsating stars used by Henrietta Leavitt in the early 1900s, are standard candles for nearby galaxies. They're bright enough to be seen out to a few tens of millions of light-years, but not much farther. Type 1a supernovae are standard candles for the distant universe. They're so bright they can be seen across billions of light-years, and because their peak brightness is so uniform, they're incredibly accurate. You can measure distances to within about 7% accuracy using Type 1a supernovae. That's better than almost any other distance measurement technique available. The discovery that Type 1a supernovae could be used as standard candles came gradually. Astronomers noticed in the 1930s and 40s that certain supernovae seemed to have similar light curves and spectra. They grouped them into types. Type 1 supernovae showed no hydrogen lines in their spectra. Type 2 supernovae showed strong hydrogen lines. Later, Type 1 was subdivided. Type 1a showed strong silicon lines. Type IB and IC didn't. Type Ia became the interesting one because the light curves were so consistent. Every Type Ia supernova looked like every other Type Ia supernova. Same rise time, same peak brightness, same decline rate. By the 1980s, astronomers realized they could use that consistency to measure distances. By the 1990s, they were using Type Ia supernova to map the expansion of the universe. Two independent teams, the Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, spent the late 1990s observing distant Type 1a supernovae. They were looking for evidence of how the expansion of the universe was slowing down. Everyone expected the expansion to be slowing. Gravity should be pulling galaxies back together. The universe should be decelerating. The Type 1a supernovae would show how much. Measure the brightness, calculate the distance, compare it to the redshift, and you'd get the deceleration rate. That was the plan. The results came in wrong. The distant supernovae were dimmer than expected, not a lot. But noticeably, dimmer meant farther away than they should be. Farther away meant the expansion wasn't slowing down. It was speeding up. The universe was accelerating. Something was pushing galaxies apart, not pulling them together. The result was announced in 1998. Both teams published within weeks of each other. The findings were confirmed by follow-up observations. The universe is not just expanding, it's expanding faster over time. The acceleration is driven by something called dark energy, a mysterious component of the universe that makes up about 70% of the total energy density and acts like a repulsive force on cosmic scales. Nobody knows what dark energy is. Nobody has a satisfying explanation for why it exists, but Type 1a supernovae proved it's real. The observations don't lie. The supernovae are dimmer than they should be. The distances are larger than expected. The expansion is accelerating. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for the discovery. The citation read, "For the discovery of the accelerating expansion of the universe through observations of distant supernovae." Type 1a supernovae didn't just confirm a prediction, they overturned it. They revealed something fundamental about the universe that nobody expected. Much of modern cosmology rests on these events: the measurements of dark energy, the constraints on the age and geometry of the universe, the timeline of cosmic expansion. All of it depends on Type 1a supernovae behaving predictably. on white dwarfs exploding at the Chandrasekhar limit with the same energy release every time, on the fact that a dying star in a binary system, accreting mass for millions of years, will eventually cross a threshold and detonate with a brightness that can be seen across the observable universe. The mechanism behind Type 1a supernovae was debated for decades. Astronomers knew the explosions came from white dwarfs. The spectra showed no hydrogen, ruling out a massive star core collapse. The light curves matched the radioactive decay of nickel-56, confirming a thermonuclear origin. But how did the white dwarf reach the Chandrasekhar limit? Two scenarios were proposed. The first is called the single degenerate model. A white dwarf in a binary system accretes mass from a companion star, usually a red giant or a main sequence star. The white dwarf gradually gains mass over millions of years. Eventually, it reaches 1.4 solar masses. Carbon ignites. The star explodes. The second scenario is the double degenerate model. Two white dwarfs in a binary system spiral inward due to gravitational wave radiation. They merge. The combined mass exceeds the Chandrasekhar limit. The merged object explodes. Both scenarios probably happen. Observations suggest that some Type 1a supernovae come from single degenerate systems, others from double degenerate mergers. The explosions look similar because the progenitor mass is the same in both cases, roughly 1.4 solar masses. The details differ slightly. Single degenerate explosions might show traces of hydrogen stripped from the companion. Double degenerate explosions might show slightly different abundances of intermediate mass elements. But the overall energy release, the peak brightness, the light curve shape are nearly identical. The universe doesn't care how the white dwarf got to the Chandrasekhar limit. It only cares that it did. Once the limit is reached, the outcome is fixed. Thermonuclear runaway, complete disruption. 5 billion times brighter than the sun. The explosion itself is over in seconds. The burning front propagates through the core at speeds close to the speed of sound in the degenerate material. That's about a few thousand kilometers per second. The core is a few thousand kilometers across. Do the math, and the entire star burns in less than a second. The energy released unbinds the star. The explosion is so violent that the debris is accelerated to escape velocity, 10,000 kilometers per second or more, fast enough to leave the white dwarf's gravity well and keep going. There's no collapse, no remnant core. The white dwarf is completely destroyed. Every atom that was part of the star is either fused into heavier elements or blown apart and scattered into space. The only thing left is the expanding debris cloud and the light from the explosion, traveling outward at the speed of light, carrying the news that a star just died. The debris expands for thousands of years. Eventually it slams into the surrounding interstellar medium, the thin gas drifting between the stars. The collision heats the gas, creates a shock wave, and produces a supernova remnant, a glowing shell of material, visible in X-rays and radio waves, marking the site of the explosion. Some remnants are famous. Tycho's supernova, observed in 1572 by the Danish astronomer Tycho Brahe, was a Type 1a. The remnant is still visible today, a roughly circular shell about 20 light-years across, expanding at a few thousand kilometers per second. The Crab Nebula is not a Type 1a remnant. It's a Type 2, a core collapse supernova. But other remnants scattered across the galaxy are Type 1a, SN 1006, a supernova recorded by Chinese and Arab astronomers in the year 1006, is one of the brightest supernovae in recorded history. It was a Type 1a. The remnant is barely visible today, a faint loop of gas expanding into the galactic halo. Type 1a supernovae don't just measure distances, they create the elements that make planets possible. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of it was forged inside a star and scattered into space by a supernova. Type Ia supernovae are one of the primary sources of iron group elements in the galaxy. The explosion synthesizes about half a solar mass of nickel-56, which decays into iron-56. That iron ends up in the interstellar medium, where it gets incorporated into the next generation of stars and planets. Without Type 1a supernovae, the galaxy would have far less iron. Rocky planets like Earth might not exist. Life, which depends on iron for everything from hemoglobin to enzymes, might not be possible. The explosion is also a cosmic recycling event. The white dwarf was made of carbon and oxygen, the ashes of helium burning in a star that died billions of years ago. Those ashes sat in a cooling ember for billions of years, locked in a crystalline lattice, waiting. Then the white dwarf accreted mass, the core heated up, the carbon ignited, and in less than a second, those ashes were transmuted into heavier elements and scattered back into space. The carbon became neon and magnesium, the oxygen became silicon and sulfur. Some of the material fused all the way to iron, the rest was blown apart and ejected. That material will drift through space for millions of years. Eventually, it'll collapse into a new molecular cloud. Stars will form from that cloud, planets will condense from the debris, and the atoms forged in a white dwarf explosion billions of years ago will end up in rocks, oceans, atmospheres, maybe even in living organisms. The universe wastes nothing. Every atom gets used. Every supernova feeds the next generation. The explosion is catastrophic for anything nearby. If a Type 1a supernova went off within a few tens of light years of Earth, the gamma rays and X-rays from the explosion would strip away the ozone layer. The planet would be bathed in ultraviolet radiation for years. Mass extinctions would follow. Life on the surface would struggle. Some organisms would survive, the ones that could burrow underground or live in the deep ocean, but the biosphere would be devastated. Fortunately, there are no white dwarfs close enough to Earth to pose a threat. The nearest known white dwarf in a binary system is Ik Pegasi, about 150 light-years away. It's accreting mass, but it won't reach the Chandrasekhar limit for millions of years, and even if it explodes tomorrow, 150 light-years is far enough that the radiation would be greatly diluted by the time it reached us. We'd see a bright new star in the sky. We'd marvel at it for a few weeks. Then it would fade. No extinction, no ozone stripping, just a light show. The white dwarf reached the Chandrasekhar limit. The carbon ignited. The core exploded. The star is gone. Completely. No remnant core sitting in the debris. No neutron star. No black hole. Just a rapidly expanding shell of gas and a fading glow. But not every white dwarf that reaches the limit explodes. Some collapse instead. The outcome depends on how quickly the mass is added and whether the thermonuclear runaway can propagate through the entire core before the collapse begins. If the accretion is slow and the core heats evenly, the explosion happens first. If the accretion is fast or the heating is uneven, the core might collapse before the burning can consume everything. In that case, the white dwarf doesn't explode, it implodes. The electrons and protons merge into neutrons. The degeneracy shifts from electron degeneracy to neutron degeneracy. The star collapses past white dwarf densities into something denser, something stranger, a neutron star. And if the collapsing core is massive enough, it doesn't stop at neutron star densities either. It keeps falling, straight through the neutron degeneracy pressure, straight into a singularity, a black hole. The Chandrasekhar limit is not just the boundary where white dwarfs explode, it's the gateway, the threshold between one kind of dead star and another. Below the limit, you have a white dwarf, stable, cooling, patient. Above the limit, you have something else, either an explosion that destroys the star entirely, or a collapse that creates an object so dense, so extreme, that the rules governing white dwarfs no longer apply. The next chapter in the life of a dead star isn't written in the slow fade of a cooling ember. It's written in the violence of collapse, in the crushing weight of gravity that refuses to stop, in the quantum limits of matter squeezed beyond recognition. The white dwarf story ends at the Chandrasekhar limit. What comes next belongs to a different kind of object entirely. The white dwarf exploded, or it collapsed. One of the two. Either way, it's not a white dwarf anymore. The Chandrasekhar limit isn't just a suggestion, it's a hard stop, a line the universe draws in the sand and refuses to let you cross while staying in the same category. Push a white dwarf past 1.4 solar masses and the electron degeneracy pressure that's been holding it up for billions of years stops working. The electrons run out of room. The quantum traffic jam that kept the star stable dissolves. And what happens next depends entirely on how fast the collapse happens and what's left to stop it. If the collapse is slow, if the core heats up evenly as it's compressed, carbon fusion ignites before the structure fails completely. The star explodes. Type Ia supernova, we covered that. The white dwarf is vaporized, every atom scattered into space, no remnant left behind. Just an expanding cloud of gas and a fading glow. That's one path, the clean exit, the complete destruction. But not every white dwarf that exceeds the limit explodes. Some collapse instead, and when they do, they don't stop at white dwarf densities, they keep going, straight through the floor. Here's why. Electron degeneracy pressure works because electrons refuse to occupy the same quantum state. Pauli's exclusion principle. No two fermions can share the same position, momentum, and spin. The electrons pile up in higher energy states, and that piling generates an outward pressure. It's strong enough to hold up a white dwarf as long as the mass stays below 1.4 solar masses. Add more mass and the pressure can't keep up. The electrons are forced into higher and higher energy states. Their velocities approach the speed of light. The pressure-density relationship weakens. At some point, gravity pulls harder than the electrons can push. The core collapses. But here's the thing. The collapse doesn't stop just because the white dwarf phase is over. The core keeps shrinking. The density keeps climbing. And at a certain point, the conditions inside the collapsing core become so extreme that a new reaction becomes possible. Electron capture. An electron and a proton, squeezed together under unimaginable pressure, merge. They combine to form a neutron, releasing a neutrino in the process. The reaction is called inverse beta decay, and it's the doorway to the next stage of stellar death. Under normal circumstances, protons and electrons don't merge, they're stable. A proton is positively charged. An electron is negatively charged. They attract each other, sure, but they don't combine. The proton is locked inside the nucleus of an atom. The electron orbits at a distance. The electromagnetic force keeps them apart. But inside a collapsing white dwarf core, the pressure climbs high enough that the electrons are forced into direct contact with the protons. The nuclei, the bare ions sitting in the degenerate plasma, are surrounded by a sea of electrons moving at relativistic speeds, and when the density crosses about 10 to the 11 grams per cubic centimeter, 100,000 times denser than a white dwarf, the electrons start getting absorbed. Proton plus electron equals neutron plus neutrino. The neutrino escapes. It barely interacts with matter, so it just flies out of the core, carrying energy with it. The neutron stays behind. This is the transition, the moment when a collapsing white dwarf becomes something else. The core is no longer supported by electron degeneracy pressure. The electrons are disappearing. They're being converted into neutrons, and neutrons, unlike electrons, don't have an electric charge. They don't repel each other electromagnetically. They pack together much more tightly. The core shrinks fast. The radius drops from a few thousand kilometers to about 20 kilometers. 20, that's the size of a small city. Manhattan is about 20 kilometers from end to end. Take the mass of a star, 1.4 solar masses or more, and compress it into the size of a city. That's where you end up. A neutron star. The density inside a neutron star is incomprehensible. We used that word for white dwarfs, and it was accurate then. It's more accurate now. A white dwarf has a density of about 1 million grams per cubic centimeter. A million. A sugar cube of white dwarf material weighs a ton. A neutron star has a density of about 100 trillion grams per cubic centimeter. 100 trillion. 100 million times denser than a white dwarf. A sugar cube of neutron star material weighs about 4 billion tons. 4 billion. That's roughly the mass of Mount Everest compressed into a volume you could hold in your hand. If you could hold it, which you couldn't, because the gravity would crush you into a smear of atoms before you got close. A teaspoon of neutron star material, about 5 milliliters, weighs roughly 5.5 trillion kilograms. That's about 900 times the mass of the Great Pyramid of Giza. In a teaspoon, you could fit it in a kitchen drawer. If you somehow placed that teaspoon on the surface of the Earth, it wouldn't just sink. It would punch through the crust, through the mantle, through the outer core, and keep going until it hit the center of the planet. The Earth's gravity wouldn't be strong enough to stop it. Nothing on Earth is dense enough to resist it. It would fall straight through like a stone through fog. The reason neutron stars can reach these densities is that neutrons pack tighter than electrons. Electrons are held apart by the exclusion principle. They refuse to overlap, but there's still space between them. The degenerate electron gas in a white dwarf is dense, but it's not solid. The electrons are zipping around at high speeds, occupying every available quantum state, but they're not jammed together shoulder to shoulder. There's room. Neutrons are different. Neutrons are fermions, just like electrons, so they also obey the exclusion principle. But neutrons are about 1,800 times more massive than electrons. They're also neutral, no electric charge, no electromagnetic repulsion. When you compress a core full of neutrons, they pack together until they're almost touching. The spacing between neutrons in a neutron star is about the same as the spacing between protons in an atomic nucleus. You're basically building a nucleus the size of a city. The density is comparable to the density inside a single atom, except the atom is 20 kilometers wide. The pressure holding up a neutron star is called neutron degeneracy pressure. Same principle as electron degeneracy pressure. The neutrons are fermions. They can't occupy the same quantum state. Pack them tightly enough and they're forced into higher energy states. That generates an outward pressure. It's the same quantum stubbornness that held up the white dwarf, just shifted to a different particle. The electrons are gone. The neutrons take over. And neutron degeneracy pressure is strong enough to support a stellar remnant with a mass of about 1.4 to 2.5 solar masses. That's the range. Below 1.4, you get a white dwarf. Above 1.4, If the collapse doesn't trigger a supernova, you get a neutron star. The neutron star is stable. It's not fusing anything. It's not burning. It's just sitting there, held up by the refusal of neutrons to overlap, cooling slowly over billions of years. Neutron stars are the second densest objects in the universe, the densest objects with a measurable physical surface. White dwarfs are dense. Neutron stars are denser, by a factor of 100 million. If you could somehow stand on the surface of a neutron star, which you absolutely could not, because the surface gravity is about 200 billion times stronger than Earth's, you would weigh more than all the mass of every human who has ever lived combined. The escape velocity from a neutron star's surface is about 1/3 the speed of light, 100,000 kilometers per second. Nothing built by humans could reach that speed. If you dropped a marshmallow from 1 meter above the surface of a neutron star, it would hit the ground with the energy of a nuclear bomb. The impact would release about 7 kilotons of energy. That's half the yield of the bomb dropped on Hiroshima. From a marshmallow, falling 1 meter, the magnetic fields around neutron stars are absurd. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, have fields 1,000 times stronger than that. A magnetar's magnetic field is strong enough to kill you from 1,000 kilometers away, not by pulling the iron out of your blood, by disrupting the electron bonds in your atoms. The field is so strong, it warps the quantum states of atoms. Your molecular structure would come apart. You'd dissolve from 1,000 kilometers away. Magnetars are rare. Most neutron stars just have fields that are merely trillions of times stronger than Earth's. Merely. Neutron stars spin fast. When the core of a star collapses from thousands of kilometers down to 20 kilometers, conservation of angular momentum speeds up the rotation dramatically. The same way a figure skater spins faster when they pull their arms in. Some neutron stars rotate once every few seconds. Some rotate hundreds of times per second. The fastest known neutron star, PSR J1748-2446 AD, spins 716 times per second. 716, that's faster than a blender, faster than a jet engine. The surface of that neutron star is moving at about 20% the speed of light. If it spun any faster, it would start to tear itself apart. The equator would bulge outward. Material would be flung into space. There's a theoretical limit to how fast a neutron star can spin before centrifugal force overcomes gravity. Most neutron stars don't get close to that limit, but some do. And they sit right on the edge, spinning so fast that the only thing holding them together is neutron degeneracy pressure and the fact that the neutrons are packed too tightly to move. The most massive neutron star ever confirmed is PSR J0952-0607. It weighs about 2.35 solar masses, give or take. That's close to the upper limit. Neutron degeneracy pressure, like electron degeneracy pressure, has a maximum. There's only so much weight you can pile onto a neutron star before the pressure fails. The exact value of that limit is still debated. Theoretical models put it somewhere between 2.2 and 2.9 solar masses. The uncertainty comes from the fact that we don't fully understand how matter behaves at neutron star densities. The strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei, dominates at those scales, and the equations that describe the strong force are messy. Physicists call the relationship between pressure and density in neutron star matter the equation of state. There are dozens of proposed equations of state. They all predict slightly different maximum masses. Observations are starting to narrow the range, but the basic point is clear. Somewhere around 2.5 to 3 solar masses, neutron degeneracy pressure stops being strong enough to hold up the star. Add more mass, and the neutrons run out of room. The exclusion principle can't generate enough pressure. Gravity wins. The neutron star collapses, and when it does, there's nothing left to stop it. No new particles to take over. No new degeneracy pressure to kick in. Neutrons are the densest stable particles. You can't compress them into anything smaller without breaking the rules of physics in ways we don't have equations for. The core collapses past neutron star densities. The radius shrinks below 20 kilometers, then 10, then 5. The escape velocity climbs past the speed of light. At that point, the object stops being a neutron star. It stops being anything with a surface. It becomes a black hole. A black hole is not made of anything. That's the key difference. A white dwarf is made of degenerate electrons and ions. A neutron star is made of neutrons. A black hole is not made of particles. It's made of space-time. The mass that collapsed into it is gone, not scattered into space, not converted into energy. Gone. Compressed into a singularity, a point of infinite density where the equations break. The singularity is surrounded by an event horizon, the boundary where the escape velocity equals the speed of light. Cross that boundary and you can't come back. Not because there's a wall, because every direction you could move leads inward. The space-time is so warped that forward, backward, up, down, all point toward the singularity. You fall forever until you hit the singularity and stop being a coherent structure. Black holes are the endgame, the final stage of stellar collapse. There's no object denser than a black hole because density stops being a meaningful concept once you compress matter into a singularity. The singularity has infinite density. You can calculate the average density of a black hole by dividing its mass by the volume inside the event horizon. For a stellar mass black hole, about 10 solar masses, the event horizon has a radius of about 30 kilometers. The average density inside comes out to about 2 times 10 to the 18 kilograms per cubic meter. That's roughly 10 times denser than a neutron star, but that's just an average. The actual density at the singularity is infinite. The number doesn't mean anything. It's a placeholder for we don't know what happens here. General relativity predicts a singularity. Quantum mechanics says singularity shouldn't exist. The two theories don't agree. And until someone figures out a theory of quantum gravity, the singularity is where physics stops working and we start guessing. The transition from neutron star to black hole is fast, not slow like the cooling of a white dwarf, not gradual like the accretion of mass in a binary system. Fast. If a neutron star exceeds the mass limit, the collapse happens in less than a second. The neutron degeneracy pressure fails. The core implodes. The radius drops from 20 kilometers to the size of the event horizon, which for a 3 solar mass black hole is about 9 kilometers. The collapse is so violent that it releases gravitational waves, ripples in space-time that propagate outward at the speed of light. LIGO, the Laser Interferometer Gravitational Wave Observatory, has detected several neutron star mergers. 2 neutron stars spiraling inward, colliding, merging into a single object. If the combined mass is below about 3 solar masses, the result is a more massive neutron star. If the combined mass exceeds the limit, the result is a black hole. The gravitational wave signal changes. The frequency climbs as the objects spiral inward, then it cuts off abruptly. The black hole forms. The event horizon swallows the signal. Nothing escapes. In August 2019, LIGO and Virgo detected an event called GW190814. A black hole with a mass of about 23 solar masses merged with an object weighing about 2.6 solar masses. The smaller object sits in the mass gap, the range between the heaviest neutron stars and the lightest black holes. Nobody knows what it was. It could have been a very heavy neutron star. It could have been a very light black hole. The observations can't tell the difference. The object merged with the larger black hole and disappeared. The final black hole weighed about 25 solar masses. The missing mass, about 1 solar mass, was radiated away as gravitational waves. 1 entire solar mass worth of energy released in a fraction of a second, rippling through spacetime, detected by instruments on Earth 400 million years later. That's the violence of these events. That's the energy scale, and it's routine. The universe does this all the time. The differences between white dwarfs, neutron stars, and black holes are not subtle. They're different classes of objects, separated by quantum boundaries. White dwarfs are supported by electron degeneracy pressure. Maximum mass about 1.4 solar masses, radius about 5,000 to 7,000 kilometers, density about 1 million grams per cubic centimeter. Neutron stars are supported by neutron degeneracy pressure. Maximum mass about 2.5 to 3 solar masses, radius about 20 kilometers, density about 100 trillion grams per cubic centimeter. Black holes have no maximum mass, no physical surface, no internal structure, just a singularity and an event horizon. The radius depends on the mass. For a stellar mass black hole, about 10 solar masses, the radius is about 30 kilometers. The density is formally infinite at the singularity, but averages out to about 10 times neutron star densities if you include the volume inside the event horizon. The order is fixed. White dwarfs are the least dense. Neutron stars are 100 million times denser. Black holes are denser still, though the concept of density stops making sense once you're dealing with singularities. You can't compress a neutron star into a white dwarf. You can't decompress a black hole into a neutron star. The transitions only go one way. Add mass and the object collapses into the next category. There's no going back. The stellar graveyard has 3 plots: white dwarfs in the first row, neutron stars in the second, black holes in the third, and the boundaries between them are written into the laws of physics. White dwarfs are the most common. They outnumber neutron stars by about 100 to 1 in the Milky Way. The reason is simple. Most stars aren't massive enough to produce a neutron star. Stars below about 8 solar masses end their lives as white dwarfs. Stars above 8 solar masses explode as supernovae and leave behind either a neutron star or a black hole, depending on how much mass is left after the explosion. High-mass stars are rare. Low-mass stars are common. The galaxy is full of white dwarfs. Neutron stars are harder to find. Black holes are harder still, but all 3 exist. All 3 are the final states of stellar evolution. And all 3 are held up, or not held up, by quantum mechanics. The quantum forces at work are the same principle applied at different scales. Electron degeneracy pressure holds up white dwarfs. Neutron degeneracy pressure holds up neutron stars. Both are consequences of the Pauli exclusion principle. Fermions refuse to overlap. That refusal generates pressure. The pressure balances gravity. The object stabilizes. Until you add more mass, then the balance breaks. The object collapses. And if there's another type of fermion available, a denser one that can pack tighter, the collapse stops at the next level. Electrons give way to neutrons. Neutrons give way to nothing. That's the progression. That's the hierarchy. White dwarfs are patient. They cool for trillions of years. Neutron stars are violent. They spin hundreds of times per second, emit beams of radiation, strip matter from companions, collide and merge. Black holes are silent, nothing escapes, no light, no sound, just gravity pulling inward, warping space-time, swallowing everything that gets too close. The three types of remnants span the range from the mundane to the incomprehensible. White dwarfs are strange but understandable. Neutron stars are extreme but still made of matter. Black holes are beyond matter, beyond structure, beyond any intuitive picture you can build. The universe sorts its dead stars by mass. Low-mass stars become white dwarfs. Mid-mass stars become neutron stars. High-mass stars become black holes. The boundaries are determined by quantum mechanics and general relativity. The Chandrasekhar limit separates white dwarfs from neutron stars. The Tolman-Oppenheimer-Volkoff limit separates neutron stars from black holes. Both limits are consequences of fundamental physics. Both are absolute. The universe enforces them without exception. You don't get a white dwarf at 2 solar masses. You don't get a stable neutron star at 4 solar masses. The rules don't bend. White dwarfs occupy a unique place in the stellar graveyard. They're the most common remnants, the longest lived, the most stable. They don't spin at relativistic speeds. They don't emit beams of X-rays. They don't warp spacetime into singularities. They just sit there, cooling, fading, waiting for the universe to end. They're the patient ones, the survivors. The objects that made it through stellar evolution without collapsing into something stranger. And they'll outlast almost everything else. Neutron stars will eventually cool and stop emitting radiation. Black holes will evaporate via Hawking radiation over timescales of 10 to the 60 years or longer. White dwarfs will still be there, cold and dark, drifting through the void, held up by the same quantum pressure that's been supporting them since the day they formed. They're not flashy, they're not dramatic, they're just persistent. And in a universe where everything else is either exploding or collapsing or radiating itself into oblivion, persistence is its own kind of victory. The white dwarf story doesn't end with the Chandrasekhar limit. It ends with the slow fade into darkness, with the long cooling, with the crystallization of the core, with the final transition from glowing ember to cold black lump of degenerate matter drifting through a universe that's run out of stars. That's the ultimate fate, not an explosion, not a collapse. Just the patient, inevitable march toward absolute zero. And that march, that final chapter, is what comes next. The white dwarf sits in the dark. It has been sitting there for 10 billion years, 20 billion, 50. The numbers lose meaning after a while. The universe around it has changed. The bright stars are gone. The galaxies have merged, collided, drifted apart. Star formation stopped trillions of years ago when the last of the gas clouds were exhausted or dispersed. The Milky Way, if you could still call it that, is a graveyard. White dwarfs, brown dwarfs, neutron stars, black holes, that's all that's left. No blue giants, no red dwarfs burning quietly in the dark, no supernovae lighting up the void. Just the cooling embers of stars that died so long ago that the concept of ago has stopped making sense. The white dwarf is still glowing, faintly. It started its cooling journey at 100,000 degrees Kelvin, bright enough to light up a planetary nebula, hot enough to ionize any atom within light years. Now, after trillions of years, the surface temperature has dropped to maybe 3,000 degrees, still warm by human standards, still radiating. But the light it emits is deep in the infrared, invisible to anything resembling an eye. If there were anyone left to look, which there isn't, they wouldn't see it. They'd need instruments, sensitive ones, the kind that can pick up the faint thermal glow of an object barely warmer than the cosmic microwave background. The cosmic microwave background, by the way, has cooled too. Right now, in our current universe 13.8 billion years old, the background temperature of space is about 2.7 Kelvin. That's the leftover radiation from the Big Bang, stretched and redshifted by the expansion of the universe until it's just a faint microwave hum filling all of space. By the time the white dwarf has cooled to 3,000 degrees, the universe has expanded so much that the microwave background has cooled to nearly zero, maybe a few millikelvin. The white dwarf, still radiating at 3,000 degrees, is one of the warmest objects left. Not because it's generating heat, because it hasn't finished losing it yet. This is the future we're talking about, not the near future. Not the far future, the deep future, the time when the universe has aged 1,000 times longer than it has already existed, when every process we think of as fast, burning, fusing, exploding has run its course and stopped, when the only thing left is cooling, slow, patient, inexorable cooling. White dwarfs are built for this era. They don't need fuel. They don't need anything except time. And in the deep future, time is the one thing the universe has in infinite supply. Leon Mestel, the British astrophysicist who first worked out the cooling rates of white dwarfs in 1952, calculated that a white dwarf takes about 1 billion years to cool from 100,000 degrees to 50,000, another few billion to drop to 25,000. The rate slows as the temperature falls. Each halving takes longer than the last. By the time you're down to 10,000 degrees, you're looking at 10 to 15 billion years. By the time you hit 5,000 degrees, you've blown past 20 billion. The curve flattens, the cooling decelerates. The white dwarf approaches absolute zero asymptotically, getting closer and closer, but never quite reaching it, because absolute zero is impossible. Thermodynamics forbids it. You can get arbitrarily close, but you can't get there. The current age of the universe is 13.8 billion years. That's not long enough for any white dwarf anywhere in the observable universe to have cooled below the threshold where it stops emitting detectable light. The oldest white dwarfs we've found, the ones that formed when the galaxy was young, have surface temperatures of about 3,000 degrees, still warm, still glowing faintly in the infrared, still radiating. They've been cooling for 12 billion years, give or take, and they're nowhere near done. The cooling process for a white dwarf, from formation to invisibility, takes somewhere between 15 and 20 billion years, longer than the universe has existed. We are living in an era when every white dwarf that has ever formed is still visible, at least in principle, if you point the right telescope at it. That era is temporary. Give it another 10 or 20 billion years, and the first white dwarfs will fade below detectability. They'll still be there, still radiating, just too dim to see. By 50 billion years from now, most white dwarfs will have cooled to the point where they're emitting almost no light, a few hundred degrees above absolute zero, radiating in the far infrared and radio, putting out less energy than a household light bulb. The universe at that point will be dark, not empty, dark. There will still be matter. Galaxies, or what's left of them, will still exist as gravitationally bound collections of dead stars. But there will be no light, no fusion, no active galactic nuclei, no quasars, no gamma-ray bursts. Just the faint thermal glow of cooling objects, and the even fainter glow of the cosmic microwave background, itself cooled to a fraction of a degree above absolute zero. If you could somehow float through that universe, you wouldn't see anything, not with your eyes. Not with any instrument that relies on visible light. The universe would look black in every direction, silent, cold, empty of anything resembling activity. White dwarfs will be among the last luminous objects, not luminous in the sense of shining brightly, luminous in the sense of emitting any radiation at all. By the time 100 billion years have passed, the universe will be populated almost entirely by objects that don't emit light. Brown dwarfs, failed stars that never ignited fusion in the first place, will have cooled to the ambient temperature. Neutron stars, which start out hot from the violence of their formation, will have radiated away their heat. Black holes don't emit anything except Hawking radiation, and the rate is so slow for stellar mass black holes that it's negligible for trillions of years. White dwarfs will still be radiating, faintly, barely, but they'll be the only game in town, the last embers, the final holdouts against the encroaching cold. At some point, the white dwarfs will cool enough that we stop calling them white dwarfs. The term white implies they're hot enough to emit visible light. Once the surface temperature drops below about 1,000 degrees, the light shifts entirely into the infrared and radio. The object is no longer white. It's not emitting in the visible spectrum at all. Astronomers have a name for this stage, a black dwarf, a completely cooled white dwarf, no light, no heat, just a lump of degenerate matter, a crystallized core of carbon and oxygen, sitting in space at the ambient temperature of the universe, a fossil, a relic, the final state of a low-mass star. Here's the thing. Black dwarfs don't exist yet, not one. The universe is too young. The cooling time required to reach black dwarf status is about 10 trillion years, 10 trillion. That's roughly 700 times longer than the current age of the universe. If the universe were a single day old, from midnight to midnight, we'd be living at about 2 minutes past midnight. The first black dwarfs wouldn't appear until sometime next week. The timescale is so long that the human brain has no framework for processing it. You can say the words 10 trillion years, and your brain will nod and file it under a long time and move on. It won't build a picture, because there is no picture. 10 trillion years is a span of time so vast that it dwarfs the entire history of stars, galaxies, planets, life, everything. And that's just the beginning. That's when the first black dwarfs start to appear. The last white dwarfs, the ones with the lowest masses and the slowest cooling rates, won't finish cooling for 100 trillion years or more. By the time black dwarfs exist, the universe will be unrecognizable. Galaxies will have long since stopped being galaxies in any meaningful sense. The stars will have either burned out or been ejected by gravitational interactions. Close encounters between stars, rare in the current universe, will have shuffled the populations over trillions of years. Some stars will be flung out of their galaxies entirely, drifting alone through intergalactic space. Others will spiral inward and fall into the supermassive black holes sitting at the centers of what used to be galaxies. The black holes will grow, slowly, feeding on the occasional stray star or neutron star that wanders too close. By 100 trillion years, most of the mass in a galaxy will either be in the central black hole or scattered into the void. The galaxy, as a coherent structure, will be gone. What's left is a diffuse cloud of dead stars, widely separated, drifting through a space that's expanding faster every year. The expansion of the universe is accelerating. This was discovered in 1998 by 2 independent teams observing distant Type 1a supernovae. The observations showed that the universe isn't just expanding, it's expanding faster over time. The acceleration is driven by dark energy, a mysterious component that makes up about 70% of the total energy density of the universe and acts like a repulsive force on cosmic scales. Dark energy doesn't affect small systems, galaxies don't expand, solar systems don't expand. But on scales of hundreds of millions of light-years, dark energy pushes things apart, and the effect gets stronger as the universe ages. By the time black dwarfs start appearing, the expansion will have carried most galaxies so far apart that they're no longer visible to each other. Even if there were someone around to build a telescope, which there won't be, they'd look out and see nothing. No distant galaxies, no stars, just blackness. The observable universe, from any given point, will shrink to include only the local gravitationally bound structure, and even that will be dark, full of black dwarfs, neutron stars, and black holes. No light, no activity, just cold, silent objects drifting through the void. White dwarfs, in this far future, will have finished cooling. They'll be black dwarfs, invisible, inert, sitting at the ambient temperature of the universe, which by that point is a tiny fraction of a degree above absolute zero. The cosmic microwave background, already cooled to a few millikelvin, will continue to cool as the universe expands. Eventually, the background temperature will drop so low that it's effectively zero for any practical purpose. The black dwarfs will cool along with it, asymptotically approaching absolute zero without ever quite reaching it. They'll sit there for trillions of years, tens of trillions, hundreds of trillions, doing nothing, radiating nothing, just existing. And then, maybe, they'll start to decay. This part is theoretical. Nobody has ever observed a proton decay. Protons, as far as we can tell, are stable. They don't fall apart on their own. The standard model of particle physics says protons are stable indefinitely. But some extensions of the standard model, theories that go beyond the current framework, predict that protons should decay eventually, very slowly, over timescales so long that they make the age of the universe look like a rounding error. The predicted lifetime of a proton, in these models, is at least 10 to the 34th years. Some models push it as high as 10 to the 36th years or longer. Either way, we're talking about a number so large that it has no meaning in human terms. A 1 followed by 34 zeros, or 36 zeros, numbers that make 10 trillion look like nothing. If protons decay, and that's still a big if, then black dwarfs will eventually evaporate, not all at once, one proton at a time. A proton decays into lighter particles, usually a positron and a neutral pion, which then decay into photons. The positron annihilates with an electron, if there are any electrons still around, releasing more photons. The black dwarf loses a tiny bit of mass. Another proton decays. Another tiny bit of mass gone. Over time, the black dwarf slowly dissolves. The process takes roughly 10 to the 38 years. That's a 1 followed by 38 zeros. The number is so large that calling it unimaginable is an understatement. It's unimaginable to the power of unimaginable. If you tried to count to 10 to the 38, one number per second, you'd need more time than the universe has existed trillions upon trillions upon trillions of times over. And that's how long it takes for a black dwarf to completely evaporate. But even if protons don't decay, even if they're stable forever, the black dwarfs won't last, because there's another process, quantum tunneling. The carbon and oxygen nuclei in a black dwarf's core, locked into a crystalline lattice, are sitting in a configuration that's stable, but not the most stable. The most stable nuclei in the universe are iron 56 and nickel 62. They're at the bottom of the binding energy curve. Everything else, given enough time, will eventually tunnel into iron or nickel. Tunneling is a quantum process where particles spontaneously shift from one state to another without having enough energy to classically make the transition. It's rare, vanishingly rare, but given enough time, it happens. The timescale for a black dwarf's carbon and oxygen to tunnel into iron is estimated at about 10 to the 1500 years. That's not a typo. 10 to the 1500. A 1 followed by 1500 zeros. A number so large that there aren't enough particles in the observable universe to represent it. A number so large that the concept of time itself starts to break. At that point, the black dwarf, now composed of iron and nickel, still isn't done. The iron nuclei can undergo further quantum processes. Pycnonuclear fusion, where nuclei fuse at zero temperature purely through quantum tunneling. The end result, after timescales that make 10 to the 1500 look reasonable, is that the black dwarf might collapse into a neutron star or a black hole, depending on its mass. Or it might just sit there, a lump of stable iron, for the rest of eternity. Nobody knows. The physics gets speculative at that point. We don't have equations that cover what happens to matter over timescales of 10 to the 1500 years. We don't even have a framework for thinking about it. The universe, in this far future, is effectively dead. Not in the sense that it doesn't exist, in the sense that nothing is happening. No stars, no planets, no life, no chemistry. No structure beyond the basic gravitational clumping of black holes and the faint, cold remnants of matter. The temperature everywhere is effectively zero. The expansion continues, accelerating, carrying the remnants farther and farther apart until even gravitationally bound structures start to feel the pull. Galaxies, or what's left of them, will eventually be ripped apart by the expansion. Stars will be torn from their orbits. Black dwarfs, neutron stars, black holes, all scattered into the void, alone, separated by distances so vast that they might as well be in different universes. The observable horizon will shrink to include only the local object and nothing else. Each black dwarf, each neutron star, each black hole, isolated completely, drifting through a space that's expanding faster than light can cross it. This is called the Big Freeze, or the heat death, the end state of a universe dominated by dark energy, where the expansion never stops, the temperature drops to zero, and entropy reaches its maximum. It's one of several possible fates for the universe. There are others. The Big Rip, where dark energy gets stronger over time and tears apart everything, including atoms, in about 22 billion years. False vacuum decay, where the Higgs field, which might be metastable, suddenly drops to a lower energy state, triggering a bubble of true vacuum that expands at the speed of light, destroying everything it touches. That could happen in 20 to 30 billion years if the models are right. Or it could never happen. Nobody knows. The current observations suggest the Big Freeze is the most likely. The universe will expand forever, cool forever, and eventually reach a state where nothing ever changes. A static, frozen, empty void. White dwarfs, in this context, are symbols, not symbols in a literary sense. Symbols in a physical sense. They represent persistence, the refusal to disappear even when everything around you has stopped. A white dwarf is what's left when a star runs out of options. It's the last stage before total collapse or total dispersal. It can't fuse, it can't burn, it can only cool. And it does that job with a patience that makes geological timescales look rushed. A white dwarf will sit in the dark for 10 trillion years, radiating away the last traces of heat from a collapse that happened when the universe was young, and it won't stop until the heat is gone. It doesn't complain, it doesn't collapse, it just waits. And in a universe where everything else is either exploding, collapsing, or accelerating into oblivion, that kind of patience is worth noticing. The irony is that white dwarfs, the objects held up by the quantum refusal of electrons to share space, the objects that sit at 1,000,000 times the density of Earth without collapsing, the objects that survive for trillions of years on nothing but residual heat, will eventually lose even that. The electrons will still be there, still refusing to overlap, still generating degeneracy pressure. The structure will still be intact, but the heat will be gone. The radiation will stop. The black dwarf will sit at the ambient temperature of the universe, which is effectively zero, and it will have nothing left to give. It will be the most stable, most patient, most enduring object in the cosmos. And it will be invisible, undetectable, forgotten, a monument to a universe that used to have stars. There's a kind of poetry in that, not the cheerful kind, the kind that makes you sit quietly for a while and think about how everything ends. White dwarfs don't go out in a blaze of glory. They don't explode. They don't collapse into singularities. They just fade, slowly, over timescales so long that the entire history of human civilization, from the first stone tools to the last breath, is less than a blink. And then they're gone. Not destroyed, just invisible, still there, still held up by quantum mechanics, but offering nothing to the universe except their own stubborn refusal to collapse. The universe in 10 trillion years will be a dark place. In 100 trillion years, darker still. In 10 to the 38 years, if you can even call that a year, it will be a void, empty, cold, silent. The black dwarfs will still be there, technically, if protons haven't decayed and quantum tunneling hasn't turned them into something else. But they won't matter. Nobody will be around to see them. Nobody will be around to measure them. Nobody will be around to care. The lights will have gone out. Everywhere, all at once. And the universe will continue expanding, cooling, thinning, until the concept of structure stops making sense, and all that's left is a faint haze of photons and a few scattered particles drifting through a space so empty that calling it a void is generous. White dwarfs are the last luminous objects, the final holdouts, the stubborn embers that refuse to go dark even when everything else has. They will outlast the bright stars, the galaxies, the quasars, the black holes, everything. They will sit in the void, cooling, fading, waiting for the universe to forget them. And when they finally do go dark, when the last white dwarf cools to the ambient temperature and stops radiating, the universe will have crossed a threshold. The era of light will be over, not paused, over. The last photon emitted by the last cooling white dwarf will travel outward into the expanding void, and there will be nothing left to follow it. The universe will be dark, completely, permanently, forever. That is the ultimate fate of white dwarfs, not an explosion, not a collapse. Just a long, slow fade into a darkness so complete that even the concept of darkness loses meaning. They are patient. They are persistent. They are the last thing standing when everything else has fallen. And in the end, that persistence doesn't save them. It just delays the inevitable. The universe doesn't care how long you hold on. It doesn't reward patience. It just keeps expanding, keeps cooling, keeps marching toward maximum entropy, and eventually everything ends up in the same place, cold, dark, silent, forgotten. The white dwarf sits in the dark. It has been sitting there for trillions of years. It will sit there for trillions more. And then, one day, in a future so distant that calling it the future is almost meaningless, it will stop. The last bit of heat will radiate away. The temperature will drop to zero. The black dwarf will become indistinguishable from the void around it. And the universe will move on, if moving on is even the right phrase, into an era where nothing happens, nothing changes, and nothing ever will again. That's the end, not with a bang, not with a whimper, just a slow, inevitable slide into nothing. The white dwarf has been sitting in the dark for longer than you can imagine, longer than numbers have meaning, and it's still there, still held up by nothing but the quantum stubbornness of electrons refusing to share space, still cooling, still waiting, still refusing to collapse even when the universe itself has run out of things to do. That refusal is what this has all been about, not the density, not the numbers. The refusal. A star dies, the fusion stops, the core collapses, and at the exact moment gravity should win, should crush everything into oblivion. Quantum mechanics says no, not because of a force, not because of heat or pressure or anything you can touch, because of a rule. A rule so simple you can state it in one sentence. No two electrons can occupy the same state. That's it. That's the entire defense. And it's strong enough to hold up the mass of a sun compressed into the size of a planet for trillions of years. There's something deeply unsettling about that. The idea that the universe's most patient objects, the ones that outlast galaxies, the ones that sit quietly in the void while everything else explodes or collapses or burns out, are held together by nothing but a principle. A quantum rule that says certain things are not allowed, and the universe enforces that rule without exception, without compromise, without caring whether it makes sense to a species that evolved on a rock orbiting a star that will one day become the very thing we've been talking about. White dwarfs are not exotic curiosities. They are the future, our future, the sun's future. The endpoint of 97% of every star that has ever existed, and they don't fade quietly into nothing. They persist, for timescales so vast that the word forever starts to feel inadequate.